Alright, hello everyone. Let me set the context. This video is going to be divided into two parts, the beginner stuff in Rust and then the slightly advanced stuff in Rust. We have already done the beginner stuff once in a longer 4-hour video. So this should have ideally been part 2, but I'm still going to recap everything we have covered in part 1. If you want a more toned down version of part 1, then you can go to the 4-hour video, it's on YouTube. If you want to recap it very quickly, if you want to, if you understand usual constructs of a language, for example, things like conditionals, loops, functions, then you can just go through this part 1, which covers all of this in 1 hour. This video covers all of this in 4 hours. Pick and choose which one is more relevant for you based on, your current level. This is going to be part 1, probably an hour to 2 hours. Then we'll go through part 2, where we will be covering some new concepts in Rust we haven't touched until now. Specifically things like vectors, iterators, hash maps. These are collections that are very commonly used in various languages, not just in Rust. How do you create them in Rust? What are the challenges that come here? Then we'll understand the difference between strings and string slices. It's a very subtle but important difference. Then we'll go through generics. We covered them a little bit in part 1. We'll recover them in part 2 on the current part. Traits, multi-threading, macros, futures, async await, and Tokyo. We'll try to cover all of this. Most probably, my current guess is that asynchronous Rust we're probably going to do in another video. It probably deserves a video of its own. So 0.8 and 0.9 that I've mentioned over here may or may not be covered in today's video. Everything else that you see over here, including lifetimes, is what we will cover. The things that you see in green are slightly easy. The things that you see in orange are not too difficult to understand. And the things that are written in red are slightly harder to digest. So, based on what section you're on, feel free to go slow, do a bunch of practice, so on and so forth. Without any further ado, let's start with part 1. Let's recap our 4-hour video. Let's go through all of these concepts one by one, kicking things off with installing Rust in our machine and doing a very basic IDE setup. What does IDE mean? Visual Code, Visual Studio Code, WebStorm, whatever is your, integrated development environment. How do you set it up for Rust? To kick things off, you have to first understand how to install Rust on your machine. The easiest thing you can do over here is go to the official page and it will give you a script that you can run on your machine. Once you run the script, Rust should be working. Let me quickly show you what that looks like on my laptop. I already have it installed. But if you look over here, this is the official Rust page. This is the command that I ran on my machine. If I open my terminal and try to run the same command again, it will probably tell me Rust already exists. It asks me to reinstall. Let me just reinstall to show everything again. I would probably go with step 1 over here. Proceed with standard installation. There we go. Rust is installed for me. How can I confirm that Rust is installed? If you run cargo over here in your terminal, if it gives you an output that looks something like this, it means you're good to go. If running the cargo command tells you Rust package manager and gives you a bunch of commands that you can run using it, then you are good to go. If you run cargo and you get an output that looks something like this, command not found, cargo, not cargo 1, cargo. If you run the cargo command, it gives you an output like this. It means you've not been able to install it correctly. So first, make sure you debug through all of these problems. Have it installed locally. How do you know you have it installed? If you run cargo, you should see something like this. Step 2 is setting up Visual Studio Code. That's the IDE that we are going to use. Feel free to, follow the same steps. Probably not the same step. If you are using WebStorm, NeoVim, Sublime Text, then the steps will be fairly different. I would assume most people here use Visual Studio Code. So over there, the steps are fairly simple. There are 3 extensions that are good for you to install, but one extension that you should definitely install, the Rust Analyzer. So in your Visual Studio Code, you might have seen this plugins section over here. Let me just show you to it. On my machine, if I open Visual Studio Code, there is this section over here called extensions. Over here, you can search for 3 extensions. The Rust Analyzer, I already have it. If I go over this, it asks me to reload, probably because I just reinstalled Rust on my machine. But you should see a button over there that says install. Make sure you install this and two more extensions which might be good for you to install. Code LLDB, this will help you to run Rust code directly from your IDE, and TOML because this is a common format for a bunch of Rust files. Harkiyat, what does format mean? Don't worry about, but basically you might have heard of JSON or YAML as two, formats for configuration files. TOML is fairly similar. Rust uses TOML very frequently, which is why it's a good idea for you to install this so you can, see color highlighting in your TOML files. That's pretty much it. That's all you have to do in the first section. That should complete installing Rust and doing the IDE setup. If you want a more detailed video, the 4-hour video is there, covers this in a little more detail. With that, let's move on to initializing a project locally. All right. Initializing a Rust project locally is fairly simple if you have Rust installed locally. There are two types of projects in Rust. One are called binaries and one are called libraries. Binaries are mostly what we will be dealing with today, and which, as the name suggests, a binary is a final binary that you run. It is like a end user application. Hakirat, what is a end user application? The backend of a website, a command line interface, an operating system, a dictionary assignment code that you might have written. Anything that you write is an end user application. And what is a non-end user application? If this is my end user application, it can use various libraries. These are called libraries. Rust lets you create libraries as well. The goal of a library is that you write reusable code that other people can use. And what is an end user application? The final thing that actually executes in production. Think of this as your Node.js project, and think of the library as something like Express. So whoever has written Express has written a library in Node.js, and whoever writes their own Node.js project uses this library in their end user application. So there are two types of projects that you can create in Rust: an end user application for which the command to run is cargo init, or you can create a library for which the command to run is cargo init -- lib. Today, most of the code that we'll be writing ideally should be a library because we're just testing code. But to avoid any complexity here, because here you have to write some tests to actually run the code. Since this isn't an end user application, you can't just run it. You write tests to run it and test your code. To avoid that complexity, today we will just be creating a binary package. How do you do it? Cargo init. Let's quickly try that out. If I go to my terminal over here, let me create a fresh folder called Rust part 2-1. Let me go to this folder and let me open this folder in Visual Studio Code. In this folder, now let me run the In this folder, now let me run the cargo init command. The cargo init command would initialize an empty cargo.toml file, and it will create a source/main.rs file. These are the two files that you should see after you initialize a binary project. If you initialize a library, then you wouldn't see main.rs, you would see lib.rs. We'll come to what that is and when you might want to do this. Today, we will create a binary package for which you run this command, it initializes a package for you. You have a main.rs file. This is where we'll be writing all of our code. Now, if this feels overwhelming to a few, if you cannot install Rust locally, the best thing you can do is just go to repl.it, which is a platform that lets you create, a similar Rust environment on the cloud, so you don't have to run it locally. Go to repl.com, click on create REPL after you sign up, select Rust as the language over here, and click on create REPL. You will get a very similar environment over here. If you look at this Rust environment, on the left, it has cargo.toml, it has source/main.rs. What do I have over here? Cargo.toml, source/main.rs. Ignore the target folder for now, ignore what cargo.lock is. Here is where we'll be writing all of our Rust code. Eventually, we will come to what is cargo.toml, why do you need it? It is similar to a Maven file in Java or a package.json in JavaScript. It has, the name of your package, the current version of your package, and all of your dependencies. Eventually we'll be getting other people's code in, using other people's modules. So we will be filling this dependencies section. Right now it's completely empty. This is where we'll be writing all of our code. If you find problems trying to write this code, go to Replit and you can write the same code over here. This is how you run it in Replit. As you can see, hello world gets printed over here. This is how you run it locally. Run the command cargo run in the VS Code terminal, and you should see hello world printed on the screen. Cool. If you saw a while back, there was a warning over here. It was just telling me, okay, this is a toml file. You should install the toml extension. Can you see the warning over here? That is why I suggested that you install the toml extension. If you do, you will see some nice colors over here. Even if you don't, that is fine. That is all that we had for this section, which is how can you initialize a project locally or on the cloud based on your, familiarity right now. If you want to do it on the cloud, that is fine as well. Let's move on to writing some Rust code next. We'll understand variables, conditionals, and functions. Fairly simple stuff. All right, let's go through variables, conditionals, loops, and functions through a bunch of examples. I think the best way to learn the syntax is by going through a few assignments and quickly solving them. The first assignment that we will be solving today is going to be write a function called isEven that will take a number as an input and returns either true or false based on if it is an even number. So this will teach you how to create a function. This will teach you how to define a number variable. This will teach you how to call a function. All three of these things. How do you do them in Rust? Let's see it first pictorically, and then we'll code it ourselves as well. This is the final code. There is a main function in Rust, which is the entry point of your application. This is the first thing that runs anytime you execute a Rust program. In here, I am saying, please print. What does this print ln macro do? This is not a function. This is a macro. We'll come to what macros are, but since there is an exclamation here, this means this is a macro. Think of it very similar to a function. It says, please print a dynamic variable. That is what these curly braces over here mean. Print a dynamic variable, the value of which is this function call. Is_even is a function that is defined here. Find the return value of that function and print it on the screen. That is what this specific assignment over here does. I have defined a function. I've printed this function call on the screen. I've defined another function over here. The function is called is_even. It takes one argument as an input, and the argument is of type i32. What does i32 mean? It means it's a signed integer with 32 bits. Harkirat, what does signed integer mean? What does 32 bits over here mean? Signed integer means it can be positive and negative. 32 bits means it follows certain constraints. It can only be as big as some number 2 raised to the power 31, and it can be greater than minus 2 raised to the power 31 minus 1, something like this. It follows some constraints like this. It cannot be an infinitely long number. It is a 32-bit number. Can there be bigger numbers? Yes, you could have a 64-bit number as well. You could write i64 here as well, but we're just dealing with smaller numbers right now, hence i32. In a different language like C++, you might see this as int. In a language like TypeScript, you might define this as number. But in Rust, you describe numbers as i32, u32, i64, u64, so on and so forth. This is unsigned, this is unsigned, this is signed, this is signed, this is unsigned. Whenever you have u, it means it's an unsigned number, which means it can only be positive. Whenever you have I, it means it can be both positive and negative. This is the argument to the function. And what does the function return? It returns a boolean. It returns whether or not this number is even. And then we have the final functional body, which checks if num modulo 2 equal to 0. Now notice we don't have parentheses over here. You don't need them in Rust. You do need them in other languages. But in case of Rust, you can add parentheses, but you don't need to. If the condition is true, if num modulo 2 equal to 0, what does modulo 2 mean? It means the remainder. Whenever num is divided by 2, the remainder that is left, if it is 0, then it is an even number and hence we return true, else we return false over here. That is the implementation of this function. We'll be coding it very soon. Quickly to recap, I am defining the main function over here. I am calling the isEven function over here. I have defined the custom isEven function, my own function over here. This is the name of the function, is_even. These are the arguments to the function. We have a single argument called num, the type of which is i32. It returns back a boolean, and this is the function body that actually calculates the final answer. That's how you write a function in Rust. This is our final implementation. Let's try to code it really quickly in our browser, in our VS Code as well. We define a function called is_even. The common practice in Rust is to, not write camel case. You might be very used to writing something like this in JavaScript, but in case of Rust, you don't write camel case. You write whatever this case is called, snake case. I think I could be wrong. You basically separate the words by an underscore. You don't have a capital letter over here. It's just standard practice. You can still write isEven, but general practice in Rust is to write variables like this. What is the name of our argument? Number. What is the type of our argument? Could be u32, could be i32, depends on what kind of number it is. What does it return? It returns a boolean. What is the function body? Okay, if num mod 2 equal to 0, then we return true, else we return false. As simple as that. And over here, if I want, I can create a fresh variable. Let answer equal to is_even of, let's say 10, and then print the answer over here, something like this. That works as well. Or I can directly put this is_even function call over here, just like I did in the slides. So feel free to do either. This is slightly more digestible code. So this is the final code that I have written. Let's try to run it really quickly. Let me open the terminal here at the bottom. And how do you run code in Rust? Cargo run. What output does it give us? It outputs, wait for it, true on the screen, because is 10 an even number? Indeed it is. Is 11 an even number? No, it isn't, which is why it returns false. What did I say? I is unsigned. If I make this, I is a signed number. I repeat, i32 is signed, which means it can be negative and positive. If I give it a negative value over here, it will still execute for me. If I run cargo run, it still gives me false over here. But if I make this u32 unsigned, what is an unsigned number? कि भाई इसका कोई sign नहीं होगा. You can't pass negative numbers over here because I made it an unsigned number. Harkirat, why would you want to make a number unsigned? You can store more data. I mean, for people who've done unsigned and signed numbers, you probably already know why this is done. The reason this is done is so that if a number can only be positive. If it's a u32 number, I can store a much bigger number over here compared to if it was a i32 number. If it was an i32 number, then one of the bits, if these are the 32 bits, the first bit is stored for the sign, which is why you cannot store as many numbers in a i32 number. You can store some negative numbers, some positive numbers, but if you have an unsigned number, then you can store many positive numbers. That is why you might want to use unsigned integers. Cool. Hopefully that's fairly simple. Let me again show you the final code. It looks something like this. And as you can see, if I give it a very big number, Rust starts to complain again. It says literal is out of range for i32. It says i32 numbers can only follow this range. So what can I do? Let's say, I was passing this maximum number plus 5, or 9, something like this. It starts to complain. It says, yeah, this is a very big number. So what can I do? I can change the argument to i64. Here I have a 64-bit number. This is a much bigger number compared to a i32 number. It's almost, many times bigger, which is why, this bigger number is also now accepted as an argument. But of course, there is a limit here as well. If I make this very big, then, it will start to complain. Okay, the integer value is too long. Cool. All right. First function is done. This is what the function looks like. Let me commit and push this onto GitHub, so you have a reference of all of these codes in a final repository. All right, I've deployed a repository. You'll find all the code for today over here, so feel free to go code by code over here, and if you're not able to code it yourself, you can just copy the code from here. This is the first code for the day, the isEven function. Let's move on. The next function that we're defining today is a function fib that finds the Fibonacci of a number it takes as an input. I'm sure the people who are into competitive programming are suddenly very happy, and the people who hate competitive programming are going to dread this problem, because it requires a very basic, Fibonacci algorithm for you to know. I keep forgetting the algorithm from time to time, but the algorithm looks something like this. Okay, Fibonacci is a series. Just how this can be a series: 1, 1, 2. Wow, it's like really thin. 1, 2, 4, 8, 16, 32. This is a series where every number is doubling up. Similarly, Fibonacci is a series that starts like this. 0 is the first number, 1 is the second number. The third number is sum of these two. 0 plus 1, what is that? That is 1. The fourth number is sum of these two. What is 1 plus 1? That is 2. The fifth number is the sum of these two, which is, what is 1 plus 2? 3. The sixth number is the sum of this and this, which is 2 plus 3 equal to 5. The next number is 3 plus 5, that is 8. The next number is 5 plus 8, that is 13, so on and so forth. It's just a series that, has some significance in the real world, but don't worry about what that is. This is how you calculate the Fibonacci series. So can you now try to code it? Can you try to code a bunch of these, variables, or this very long pattern, such that you have to eventually write a function that finds the Fibonacci of a number it takes as input. For example, if the input is 3, then you have to find the 0th, 1st, 2nd, 3rd number in the Fibonacci series, that is 2. If the input is 5, then you have to find the 0th, 1st, 2nd, 3rd, 4th, 5th element in the Fibonacci series, so on and so forth. It takes an index as an input, could be any number between, let's say, 1 to 200, and you have to find, that specific Fibonacci number in that pattern. Cool. The code looks something like this. I've already written it for you. Ignore the main function, it does nothing over here. But if you notice the function below, it is a function called fib. I've defined a function, the name of which is fib. It takes a number as an input over here. It first defines two variables, first and second. Both of these are mutable variables. This is something new I'm introducing a little early. Mutable variables are variables whose value you can change. Think of them as non-constants. I repeat, these are non-constants. Any variable that you define in Rust by default is a constant. Just like in JavaScript, you write const a equal to 1, and then you cannot change the value of a at all. Similarly, in Rust, every variable that you define, you cannot change its value unless you add the mute identifier here. So let mute first equal to 0, let mute second equal to 1. I have some base conditions. If num is 0, return the first element over here. If num is 1, return, 1, which we know by default, is the first answer. So these two base cases we have hard coded. If the first element is wanted, return 0, second element is wanted, return 1. And then after that, we basically run a for loop for I in 1 dot dot num minus 2. Go from 1 to num minus 2. Basically, this is the first answer, this is the second answer. And every answer after that, third, fourth, fifth, sixth, we calculate by running this for loop. And what do we do over here? We first create a temporary variable called second. I repeat, if in the first iteration, what will happen? Let's dry run this. 0 is the first element, 1 is the second element. First contains 0, second contains 1. What are we doing in the first iteration over here? We are saying temp equal to second. So we are creating a new variable called temp. We are storing 1 over here. So temp will be equal to 1. Then we say second equal to second plus first. So what will second become? Second will become this plus this, which is again 1. And what does first become? First becomes temp, which is, this thing over here, 1. So what do the first variable and second variable get replaced with? The first variable gets replaced with 1. The second variable gets replaced with 1. We have slowly moved on to the next two elements of the series. That is how we're implementing the Fibonacci algorithm here. Fairly common algorithm, you'd probably do the same way in various other languages. What will happen in the next iteration? In the next iteration, again, temp will be redefined. We will be redefining the temp variable. First will be 1, second will be 1. After the first iteration, what will the two variables be? After the first iteration, first will become 1, second will become 1, and then we set temp equal to second. So this 1 value will go to the temp variable, and then, you get the idea. Second will become second plus first, which is equal to 2, and then first will become second, which is equal to 1. And then finally we return second when we're done iterating. After we iterate a few times, let's say the user wanted the 100th element, we keep updating the value of first and second. First and second pretty much, keep going up this chain. Okay, first and second are first, this value and this value. Then they become 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 this value and this value. Eventually the final value is what we return. That is how we have written the Fibonacci algorithm over here. To recap, I've defined a variable called first, which is a mutable variable. What does mutable variable mean? It can be changed. Then I define a variable called second. Then I check, is there the input element 0? Then I return the first value, or return 0 over here. Is the input 1? Then I return 1 over here. Then we run a for loop. This is one of many ways to run for loops in Rust, which is for I in the range that you want to run it through, and then do whatever you have to do, finally return the value. That is how we've written it. This is our final algorithm. Before we move to the next slide, let's quickly code it. Shouldn't take too long, probably less than 5 minutes for you to code. I know you're a coding monster. Probably will take me like, maybe 10 minutes. So let me quickly write this. What are we doing? We are writing a function called fib. What does it take as an input? It takes a number as an input, which is, an unsigned or assigned integer. This can actually be unsigned. This will always be a positive number. So, you don't have to worry about making it signed. In the main function, I'm going to write println, let's say, fib of 10. And what was the code over here? I defined two mutable variables. Mute first equal to 0, mute second equal to 1. And what did I do next? If num is 0, then I would simply return first. If num is 1, then I would return second. And lastly, as you can already see, I have some warnings over here. Okay, why do you have extra curly braces over here? So you can get rid of them. And what is the other problem I have right now? I haven't defined a return type over here. So let me give it a return type. Again, this can be an unsigned number because it will always be positive. Return second. And then lastly, what are we going to do? We're going to iterate for I in 0 dot dot num minus 2. Let temp equal to second, second equal to second plus first, first equal to temp. And then we finally return the second variable over here, and we're good to go. That is how we write the Fibonacci algorithm. We don't use I over here, so it is giving us another warning. So you can write for underscore in 0 dot dot n minus 2. Since we are not using this variable, there is no point of defining it or giving it some value. If you give it a I value, it will give you a warning. It will still compile, but this is better practice. So just replace it with underscore. Cool. This is what our final code looks like. Feel free to take a pause and try it out. Code it yourself. Let me quickly run this locally. Cargo run, and you see what's printed on the screen is 34. I would assume that is right. I have no idea. I hate the Fibonacci series since years, but let's try a number that I think I know of. The answer for fib of 4 is indeed 2, is it? Let's see. Yeah, fib of 4 is 2. I think that, well, fib of 4 is not 2. Fib of 3 is 2. This should probably be num minus 1. You get the idea. Debug the algorithm. Most probably it needs to be num minus 1 and not num minus 2. That looks much better. Yeah. Fib of 0. Let me just write it down for you. Fib of 0 is 0. Fib of 1 is 1. Fib of 2 is 1. Fib of 3 is 2. Fib of 4 is 3. So fib of 4 should be 3, which means my logic was a little incorrect. I need to iterate from 0 to num minus 1 and not num minus 2. Cool. Let's proceed. The next problem, the last problem for today. Well, the last problem for the basics is going to be write a function called get string length that takes a string as an input and returns its length. This one's, I would assume, fairly straightforward. If you know how to define a string, there are various ways to define a string. The one that we're going to use is the simplest one, which is, if you look at the main function over here, let my string equal to string colon colon from hello world. This is one way to define a string by using the string type that Rust provides you. There are various ways. We will come to the more complicated ways in the second section. We define the string. We call a function called get string length chars. We pass the string as an input. The input comes over here. We return the final value over here. This is an implicit return, by which I mean I don't write return followed by the final thing over here and put a semicolon. I don't do that. I just write the final thing. It is implicitly returned from the function. That is one complicated thing we've done over here. I repeat, what is the complicated thing? I haven't written return over here. I haven't put a semicolon over here. If you don't do that, it's the same thing. If I don't put a semicolon here and don't write the return statement here, it is still implicitly returned from the function. s.chars is a function that returns you all the characters of the specific string, and .count returns you the total number of characters. That is, the function call that we have done over here. So we are relying on this string type over here to, get the characters and get the total count. That is one complicated thing over here. The other complicated thing is the type. If you notice, the type is not string, it is @stir. And if you remember from the beginning of the class, so we are going to learn about this very soon. What is the difference between a string and a @stir? To keep things simple, I'm going to just replace this with a string in the final code over here where I'm going to write. But I hope this is clear. If not, this will actually be coming very soon when we'll understand the difference between references, ownership, borrowing, things like these. All right, let's try to code it. I'm going to define a function called get stir length that is going to take. I'm going to just take a string as an input. There are various things that happen differently if I write string over here, if I write @string over here, if I write @str over here. We're going to discuss all of these eventually when we reach, the borrowing and ownership section. But before that, I'm going to keep it simple. What did we write? str.chars, which returns you all the characters. .count will return you the count of this specific string or the number of characters in this specific string. And I'm going to change the return type to be whatever the return type of this is, which is usize, which is a smaller number, I think, compared to i32. Then I'm going to define a string over here, function let name equal to string from Harkirat. And then I'm going to say let length equal to get underscore string length for this string, and then I can just print it. The length of the string is len, and that's it. That's all that was expected. The only thing to learn was this. The other thing to learn was references, but we haven't gotten there yet, so let's not worry about that. Very simple function over here that implicitly returns this. If I want, I can write this here as well. It's the same thing. All right, let me run it. Cargo run. It says, wait for it. This is one of the reasons that Rust is ridiculed so much. The compilation times are really high. The length of the string is 8, so we're good to go. Let's proceed. Let's understand next. What are structs? Why are they used? We understand some basic primitives like strings and numbers now. Let's understand what are structs. Why do you use structs? How can they make your life a little bit easier? All right, let's understand structs next. Structs in Rust are actually very similar to structs in C++. They let you structure data together. Basically, if you have a use case like this, where you have a user who can be active on your website or not based on, let's say they've verified their email or not. And they have a username, they have an email, they have the total number of times they've been signed into the platform. Then it's a good idea for you to structure all 4 of these into a single object rather than having 4 different variables: user1 active, user1 username, user1 email, user1 sign-in count. Having a single variable, something like this, let user1 equal to a struct of type user, and these are the 4 values of that user. The user is active, this is their username, this is their email, and this is the number of times they've signed in. This is how you can define a struct so that you have all of these values for a single user in a same place. They are similar to objects in JavaScript. If you've used objects in JavaScript, you've probably seen something similar. Okay, you define something like this. Okay, let user equal to an object where you write username, something, password, something. Similarly, struct in Rust lets you first define what is the type of this structure going to be. Then you can declare various variables on top of that structure with dynamic values, different values. And if you want to print the details of a user, for example, if you want to print their username, you can access it by user1.username. That is how you create a variable or create a struct. Let's quickly try to code this. I would assume this is fairly simple to code. I first define a variable here called, or a struct here called user. What are the properties? Let's say for us over here, it's going to be first underscore name, which is a string, last underscore name, which is a string, and age, which is going to be a number. And over here, I can now create an instance of this user object. Let user equal to user with the first name being string from Harkirat, last underscore name being string from Singh, and then the age being, let's say, whatever, 32. Just saying hypothetically. That's how you define it. And how can you print it? Based on whatever you want to print. For example, if you want to print just the user's name, that's how you can print the user's first name. If you want to print their last name, you can write something like this. Harkirat, can I print the whole object? Something like this. You cannot, as you can see, but eventually when we will understand a few extra things, macros and traits, then we'll understand how can you implement the debug trait on user. What does implementing a debug trait mean? We'll get to that's the new things we're going to learn. But long story short, you cannot simply print it. The println macro does not know how to print this user structure. It has no idea. Okay, how should I print it? It has no default printing implementation, which is why you can still print the first name or the last name, because the println macro knows how to print a string. It does not know how to print a random struct, which is why this is going to give you an error. If I write this code, it clearly also shows me that last name and age you have defined, but you are not using them at all. Are you sure you need them? So, Rust will give you warnings like these from time to time. If I run this code, what do you think gets printed on the screen? A few warnings get printed to begin with. The code is still building, and then eventually Harkirat gets printed on the screen, which is exactly what I had printed over here. Cool. That's hopefully fairly simple, nothing too complicated over here. Some standard questions you might have is, Harkirat, can I make a field optional? Can I make age is, you can either provide age or not provide age? And the answer is yes. We'll come to that very soon when we reach enums. You can make some of these fields optional. How do you do that? We'll be coming to very soon. Cool. That's structs. The other important thing around structs is that you can implement functions on structs. The closer comparison between structs and JavaScript is that structs in Rust are actually more closer to a class in JavaScript. This is the sort of on-site session I did in Bangalore as well. I'll probably post a video right after this if this felt a little overwhelming. Struct specifically, there's a much more beginner-friendly in-person workshop that I took where I explained the same thing. But long story short, if you want to compare structs to something in JS, they are closer to objects, but they're more closer to classes, because classes have methods associated with them. Classes have static methods associated with them, and both of these things you can do in Rust as well, or specifically, both of these things you can do using structs in Rust. To kick things off, let's understand what I mean when I say implementing structs. We have defined a struct. I just defined a user struct over here. We have defined a rectangle struct which has a width and a height. But this isn't enough. You might want to find the area of a rectangle, a very common use case. You might have to find the circumference, the length of the rectangle. How can you do that? You can write your own implementation, or you can attach the implementation to the struct itself. You can attach a function to the struct. You can implement something on top of the struct, so that whenever someone defines a struct that of this rectangle type, they will automatically get access to this area method. I am defining a method. I am attaching that method on this struct. I am implementing some functionality on top of the struct. This is the rectangle struct. This is me implementing a function on top of the rectangle struct. The syntax of this might feel a little complicated. Specifically, if you look at the arguments, they look very weird. Function area, name of the function is area. The argument is very weird. At self, God knows what this is. It returns a number, and if you look at it, it's an implicit return, self.width into self.height. Can you already guess what this is doing over here? This function is being implemented, but it has some extra things over here. self.width, self.height. Let's see what these are very soon. But given this does implement a function on top of a struct, whatever that means, this is how you can use that function. I have now defined a rectangle struct, and I can call rect.area on this struct so that I don't have to rewrite this logic. It is already written for me over here in a single place. Let's try to understand this a little bit more. Let's understand what the self variable is over here. All right, I've written some code over here, defined the struct called rectangle or rect, has a width and a height over here, implemented the rectangle struct, added the first function here. If I want, I can add another function called, let's say perimeter, which again will have the self as the first argument. What self is, we're coming to very soon. Will again return I32. And what is the perimeter of a rectangle? It is 2 into self.width plus self.height, right? That is how you calculate the perimeter of a specific rectangle. It's the width plus height plus width plus height. I can print that over here as well if I want. Question is, what exactly is this self argument that you see over here? And the answer is, this is similar to this in a JS class. If you have ever created a JavaScript class, let me quickly show you what the syntax of that looks like. You have a class called rectangle, which has a constructor, if you remember, which takes, a width and a height as an input. And here you do a this dot width equal to width and this dot height equal to height. And then, you can define a function called area where you do return this dot width into this dot height. For the people who are comfortable with JavaScript, this is how you create a class in JavaScript. Java classes are also fairly similar. So this variable that you see, which is, the current object, this is how you define a class. How do you create a variable of the class? You do something like this: const rect1 equal to new rectangle with the width and the height. That's how you create a new variable or a new object of the class. And then you can call rect1 dot area to, let's say, print the area on the screen. That is how you would create a class in JavaScript. The constructor actually constructs the class whenever you call new rect. And then when you call dot area, it just calls this function which returns this thing over here, which is going to be the area of the rectangle. You log it on the screen. This variable over here, which is the current object, which has the height, which has the width, the corresponding width and the corresponding height of this rectangle. That is what this variable is over here. And similarly, in this implementation, think of this implementation block, which has the area function and the perimeter function, similar as this code block right here, where we have defined an area function which returns this dot width into this dot height. What are we returning here? Self dot width plus into self dot height over here. Over here, 2 into self dot width plus self dot height. This self variable is the current struct. Whatever struct you are trying to call dot area on, dot perimeter on, that specific struct comes in this @self variable. If you want to pass some extra argument over here, let's say, perimeter, I don't know, 1, which, let's say this number means something. So you can have that as the second argument here. Okay, num colon I32. So you can get access to the first argument from here as the second argument over here. You will still need to reserve the very first argument for the @self variable. That is how you create or attach functions to a struct in Rust. And you might have a question, Harkirat, can I define a function without @self? And the answer is you can define a function without @self. Let's say I've created a function called debug over here. Now I have 3 functions. The first function just takes @self as an input. The second function takes @self and also takes a number as an input. The third function takes nothing as the input. So the first 2 functions can be called on the rect1 object. They can be called on an instance of the struct. Rect1.area can be called without any arguments because there is no argument after the first argument. First argument You don't have to explicitly pass over here. You don't have to do this. It automatically comes over there. Same is true for rect.perimeter, but since it expects a second argument here, you have to pass that over here as the first argument. Again, you don't have to do rect1, comma 1 over here. You just have to pass the at self comes implicitly. This argument you have to pass explicitly. And lastly, the third thing, the debug function that we wrote. Can I call it? Can I call rect1.debug? And the answer is no. The Rust compiler will begin to complain. What does it say? It says no method named debug found for the struct rect in the current scope. It does not find a function. Here there is a function. There is. But since it doesn't have at self as the first argument, you cannot call it on the rectangle object. You can call it directly on the struct. You can call rect : debug. Something like this. This is similar to a static function in Java or JavaScript. If you remember, if you've done classes in JavaScript, you can define static functions over here. Let's say I define a static function called debug. And this static function I can call directly on the class. I can call it on the class variable, not on an object. I'm not calling rect1.debug. I'm calling capital R rect.debug, which means this is a static function. What is a static function? A function that isn't attached to the object but directly to the class. And similarly over here, if you define a variable that doesn't have at self over here, that is similar to a static function, you directly call it on the class over here. Cool. Let's see if that works as expected or not. If I run this, you will see 3 lines of code should get printed. Area is 200, perimeter is 60, debug is 1. So the third one, as you can see, I did not call rect1.perimeter. I called rect : debug because this debug function exists not sort of as a static function. It is not attached to the rect1 argument over here. Hopefully that's clear. That's all I had for structs. I added some extra things from the on-site meetup as well. So hopefully, this is straightforward. I don't have to add that video over here. Next up, to quickly recap, this is how you define a struct. This is how you implement a function on top of the struct. This is how you define the struct or declare the struct. This is how you call a associated function of that specific struct. Structs are done with that. Let's move on to enums next. All right, let's get into enums next. Enums again are a language agnostic concept. They exist in TypeScript as well. What do enums let you do? Enums let you enumerate through various types of a value. Slightly jargony statement, but it basically means if you have something that can only have certain amount of types, for example, a direction can only be one of north, east, south, or west. Or let's say you have a shape which can only be either a circle or a square. Then in this case you use enums. They let you enumerate through various types of an object. Let's say an object can be either the north direction or the east or the south or the west direction. You can totally, describe this as a string. For example, something like this, north. But the problem is if you use a string over here to describe the direction, then you can, have another direction like YouTube. Even though it doesn't make sense for YouTube to be a direction. When you know something can only be of a few types, for example, direction, it makes sense to use an enum than using a string. Let's see this a little more practically. Over here, I have defined a function called main, where I say let my direction equal to direction : north. What do I say? Okay, here is an enum called direction, and the my direction variable is not a string called north. It is not a string called north. Its type is not string. What is its type? Its type is this enum over here, which means it can only have one of 4 values. It can either be north or east or south or west. If you are creating a game, let's say in the Rust lang or generally the backend of a game, there are only 4 directions that the player can move, let's say. Then it makes sense for you to use an enum to describe one of these 4 directions. Can you still use a string? You can. You can still, say let my direction equal to north. But why is an enum better? There are multiple reasons. One, a string will take a lot of space. Enum can take much lesser space since it only has 4 variants. But more practically, or the better reason is, okay, your code is much more type safe. Your code is much more compile time safe. Okay, this variable can only take one of 4 values. We cannot put some random value in here like YouTube, like I said a while back. That is why you might want to use an enum. You define the enum variable over here. I don't know why I did this declaration, completely ignore this line of code. And then I, let's say, call a function called move around. And what does the move around function take as an input? It takes direction as an input. What is the type of the input over here? It is this direction enum. It is not a string, which means this can have only one of 4 values. Your function implementation can be much more safer now, considering the input can only have one of 4 values. Versus if this input was a string, then someone could have sent in a random string to this function. That is why you want to use enums. If something can only have 5 types, 3 types, 2 types, 10 types, then use an enum, restrict whoever is calling a function on that specific type to one of those 4 types. That is why you might want to use an enum. Let's quickly code an enum before we proceed. I'm going to define an enum called shape, not direction, shape. And let's say, there are 2 shapes that our current platform supports. Let's say we have a canvas like platform where you can create rectangles and circles. So I'm going to create 2 variants of shapes that we currently support. That includes a rectangle and it includes a circle. Given these 2 shapes, I first define a variable called, let's say, my underscore shape, which is of type, let's say, the rectangle. And then I say, I'm going to define a function called, let's say, print underscore area, which is going to take what as an input? It will take a shape as an input and it will eventually print its area. Right now, we don't have any values associated with the rectangle variant or the circle variant, which is why right now it won't be able to do much. Let me just print, something like hi there over here. But eventually you will see how can we add values to various variants. And once we have added values to various variants, how can we use those values here to print, let's say, the area of a specific shape. What have we done to recap? I have created a function called print underscore area that takes an enum as an input. This enum can have 2 variants right now, either a rectangle or a square. And we can be sure whenever this function is being called, it is being called with one of these variants, either with a rectangle or with a square. I cannot call print underscore area of, square over here because square does not exist as a variant over here, but rectangle and circle do, which is why I can write something like this shape : rectangle, and the program, compiles correctly. Or, if I want to use this my underscore shape variable, I can use that as well. If I run this, you will see a bunch of warnings because we're not using this variable right now. But I see hi there printed on the screen because this function gets called with the right arguments. The type of the argument is correct, which is a shape. The problem with this is we have not yet attached any values to a rectangle. A rectangle should ideally have, a width and a height. A circle should ideally have a radius. I have not assigned both of these things to these variants. How can I do that? Can I have an enum with associated values? And the answer is yes. Rust lets you do that. We can have enums with associated values. As you can see, I have defined an enum over here which has 3 variants. It can either be a circle or a square or a rectangle. If it is a circle, it will have one input, which is floating point 64 bits. Basically means it can be a decimal and it can be a very long decimal because it uses 64 bits. Same thing for a square. A square can have a side which is f64. Rectangle can have 2 sides. That is how I have defined my enum. Each of these variants has some values associated with it. The circle has a radius, square has a side, rectangle has a width and a height. Now if I want, I can define the variants like this. I can't write shape : circle. I have to give it one value. If I'm defining a rectangle, I have to give it two values over here. Let's code this out really quickly. Given we have an enum which has two variants, we want that the rectangle can have two sides. So it will have two values associated with it, an f64 width and an f64 height. And the circle will have a radius associated with it, which is also f64. Now, if I go to my main function, how can I define a rectangle shape? I can define the rectangle shape similar to how I was using the enum until now, but I can pass in two values now, the width and the height of the rectangle. And if I want to create a function called calculate area, that will take, let's say, the shape as an input. I can call calculate area on the specific rect shape over here. The only problem is I see an error. It says these are probably not f64s. So if I add something like this, then we're good to go. It was interpreting them as integers. 1.0 makes it a floating point number. That's how you can, define enums with some values inside. Question is, how can I access its values, Harkirat? Can I do rect dot 0 or can I do rect of 0? How can I get the first value of this specific shape? And the answer is, by using something called pattern matching. This is something that's going to come next, but let me just quickly introduce it. If this function is actually supposed to do what it's supposed to do, calculate the area of a rectangle, how can you do that? It is going to take a shape as an input, which means it could take a rectangle as an input. It could also take a circle as an input. We don't know inside the function what exactly is coming. It could be a circle or it could be a rectangle. Calculate area can be called on either one of these two shapes, and hence we first need to check what is the type of this thing. Is it a rectangle? And if it is a rectangle, then we can destructure its values here and find the final return value as a into b. That is going to be the area of the rectangle. If this is a circle, then we can destructure its radius and return 3.14 into r from here. And we can store the final value in a variable called area, let's say. We can return area from this function. And I'll also change the return type of this function to be f64. That is how you can define a function called calculate area, which takes an enum as an input, and based on what variant of this enum is it a rectangle or is it a circle, it will print either the area like this, a into b, width into height, or it will print the area like this, which is 3.14 into radius. That's like the area of a circle, right? I think so, pi r square. Cool. Can you do other things? You can implicitly return the value directly like this as well. This also works. This basically means, okay, I'm going to return this from this specific function, which in the end returns either a into b or 3.14 into r. What is this syntax called? It's called the pattern matching syntax. Okay, given an enum that is going to have, let's say, 4 variants or 2 variants, based on what variant this specific variable currently is the shape a rectangle? If it is a rectangle, then you call a into b. If this is a circle, then you call 3.14 into r. Cool. That is what pattern matching is. If we go back to the slides here, what did we say? Enums let you enumerate over various variants of a specific type. For example, a shape can have 3 types: circle, square, and rectangle. This is how you define the circle. It takes one value as an input. This is how you define a square. This is how you define a rectangle. And if you want, you can also eventually pattern match on these various variants, irrespective of whether they have values or not. And based on that, run certain conditions or, do certain things based on which of these branches finally gets called. If it's a rectangle, then this branch of code will get called. If it is a circle, then this branch of code will get called. The circle has an associated radius over here. The square has an associated side. The rectangle has an associated width and height. That's how enums let you enumerate with values. Let's move on to pattern matching. I've already discussed this. So what is pattern matching? Okay, given this calculate area function that takes a shape as an input, how can you implement its body? We already saw it. We already saw it over here where I implemented the body by pattern matching on various variants of this specific enum. The same thing is being discussed over here. Okay, the calculate area function will pattern match on the shape, and if it is a circle, the answer would be you can get the pi constant from the Rust library into radius. If it is a square, then it will be side length into side length. If it is a rectangle, then it will be width into height. The match statement that is used over here is to match across an enum, and then these are the 3 branches based on what kind of this enum is. Cool. Hopefully that's straightforward. Returns the result implicitly. Hopefully the syntax is clear. Okay, I did not have to add a return statement over here, did not have to put a semicolon over here. I implicitly returned this specific match statement, which in the end returned either this or this or this based on the variant of the enum. That is what pattern matching is. Next up, let's understand 2 important enums. This will probably give you more clarity on why do you need enums. There are some enums that you can define on your own. For example, over here we defined this the shape enum which had 2 variants. There are some enums that Rust provides you by default, specifically the option and the result enum. Let's understand what these are, why they are useful. Let me give you a TLDR. They are used for, number 1, to have null points. I wouldn't call them null pointers, but like null values is probably a better way to say it. Null values in Rust. And number 2 for error handling in Rust. Error handling and null pointers in Rust are done via enums, specifically the options enum and the results enum. Let's go through what both of these are next. Let's get into the very first enum for today, the options enum. This is something that the Rust library provides you. And what does this let you do? It lets you return none or null or nil values from a function. If there is a function that can either return, let's say there's a function called sum that can either return a number, something like return 1, or it can return something like null, then what this function should return is an option. What does an option mean? It means it can either be some value, it can either be some value like 1, or it can be none value, it can be no value. If you were writing the same code in TypeScript, you would write it something like this. Okay, there is a function called sum which returns either a number or a null. And then in the function body, you would either return a number or a null. If there is ever a function that will return either a concrete value or null, which means this function wasn't able to do what it was supposed to do. Harkirat, can you give an example? Yes. A good example of this is, let's say there is a function called find underscore first underscore a, and it takes a string as an input. I repeat, the function is called find first a, which takes a string as an input and returns the index where the first a appears. For example, if the input to this is Harkirat, then the answer would be 1 because at the first index a appears. If the input to this is Raman, then the answer from this function should be 1 because at the first index a appears. But if all Punjabi names in my head, Preet. If the input is Preet, does a appear anywhere over here? It does not. So what should this return? You might say, Harkirat, if a is not found, then you can return -1. Sure, that is one way to do it. That is one way to return null values from a function, but it's better to formalize it. Okay, if there is a function that is not returning anything, if what you were supposed to find over here, which is the first a in a string, you were not able to find that, then simply rather than returning -1, return something better. You might say, Harkirat, okay, then let's just return null. Hopefully Rust has a null value, but the answer is Rust does not have a null value. They explicitly chose, okay, we will not have nulls. I don't know if you've heard of this, but JavaScript says the $1 billion mistake was introducing nulls or undefined into the JavaScript language. And hence, even in Java, you might have seen a very similar thing. In Rust, you have the options enum, which lets you do what? The options enum lets you return either some value or none value. ignore what this enum looks like. I know it looks a little complicated right now. This is what the enum actually looks like. It might look very similar to what we've written until now. We wrote enum rectangle and it had 2 variants. These guys have also written something similar, enum option, but there is some extra syntax over here that's hard to digest. There is, some t variable over here, which I don't know what this is. So ignore its definition for now. We will eventually understand this when we learn about generics. For now, ignore this and this. Ignore the whole definition of an enum. Let's see how you can use the options enum. Let's define our own function called find first a, which returns you the very first a given a string. Let me quickly write this for you. What do we want to do? We want to define a function called find first a, which takes a string as an input and returns the very first character, the index of the character where a appears. How can you do that? You can enumerate through the string and find the very first character. For example, let answer equal to -1. I've written a function called find underscore first underscore a. It takes a string as an input, returns an i32 number for now. I32 number meaning a number which can be negative as well as positive. It is a signed number. It is not an unsigned number. It is not an unsigned number. It's a signed number. What does the logic do? You probably don't need this anymore. It iterates over all the characters of the string. If the input is Harkirat, then it will iterate over H, A, R, K, like that. It enumerates or iterates over all the characters. If it finds the a character, it returns that specific index. If it does not find that specific character ever in this for loop, it will finally return -1. This might feel like it's decent logic. You can always do this. Okay, let index equal to find first index for the string called Preet, and you can write if index equal to -1, then you can print a not found, else you can print the other thing, which is going to be index is index, something like this. You might think this is decent logic. This is actually not too bad, but what is the problem? The return type is a little messed up. It's not very descriptive. It is a number which has a value of -1. How can the index of something be -1? You might say, Kirat, if it is not present, it is -1. Sure. You can always argue this, okay, this is better. But usually it's a good idea for you to be able to return a null type. Here I want this to either return some value or return a null value. I want my function to either return one of these two. It should be very descriptive. Here nothing came back. Not -1. We'll have other use cases in the future that also might not return anything. Their return type might be a string. What will you return over there? An empty string. So it's just a good idea to formalize a null value in a language, but Rust does not have a null value. What does it have? It has options. So let's understand, how can I replace the return type from being a number that is -1 if the value is not found to something better? How can I add a nullable value over here? The answer is by returning the option of type i32. I repeat, I'm not returning i32 over here. I'm returning an option of the type i32. We'll very quickly dig into, what this option type is. What does this enum actually look like? Why does it have a T over here? We'll get to that. But before we get there, what have I done? I've changed the return type to be option of i32. And now if I do find it, if I do find the value, I return the sum variant. Sum means कि कुछ value वहाँ पे, there is some value over there. The sum variant of this option enum. What is option? Option is also an enum only. Just like we defined the rectangle, option is also an enum. It looks slightly weird. It has a T over here. But this enum, has two variants, the sum variant and the none variant. So whenever you want to return null or nil from a function, the better way to do it is not return -1 or an empty string, return an option of the actual return value, so that this index over here if you look at it, has an option of I32, which means it can either be an I32 number or it can be none, or no value at all. And over here, rather than adding an if else check, what do you think we can do? We can pattern match on this enum. Here, pattern match on the enum. If it is some value, then just print the index is that specific value. And if it is none variant, then you can print a not found. Is that digestible? What have I done? I've said the find first function is going to return the option of an I32, which can have two variants. This is an enum which can have two variants. What does option look like? It looks something like this. Enum option. It has a sum variant, which in our case is an I32 number. It has a none variant. This is what our option, this thing looks like. Enum looks like, because our option enum is for a I32 value. In fact, I can do this. Yeah, you should probably name this something else. I'll call it custom option. It is going to return a custom option. And over here, I'm going to write custom option : sum, this thing, custom option : none. This might have confused you a little bit more, but let me still try to take you through what I've done over here. I've defined my own custom option, which can have two variants. In the end, the option enum is also the same. It is defined somewhere else. If I go to this file, you'll see pub enum option. It just has a very weird syntax we haven't discussed until now, which is called the generic syntax. We will get to that later, which is why I've just trimmed down this option enum in my own implementation to have a none variant and to have a sum variant, which is of type I32. This is what I've done. I've just changed the option enum, the official option enum, to my own implementation so that it looks something like this. Just how I had defined a rectangle which had, shape which had two variants, a circle which had a number as an input and a rectangle which had a two numbers as an input. I have defined the option enum, which also has two variants. None means bhai kuch return nahi hua, this function returned nothing. Sum means it returned some value to you, which in our case is a number, but in the future it could be a string, it could be two numbers. We can define what the return type of our function is. Since our function right now is find the first index, it returns us an option which returns the I32 value. But in the future it could be, a string that our function returns. What if the function was find the first word? I repeat, what if the function was, I ask you to write a function find underscore first underscore word. It takes a string as an input. So in this case also, you have to return an option, because what if the string is empty? If the string is empty, then there is no first word. Then, you should return a null value in that case also. So find first word will also return an option, but this will return an option of a string, and our thing returned an option of a number. And just to make it even more simpler, I sort of defined our own enum called option, but let me not do that. Let me revert everything. Let me take you back through the original implementation that I had written, which looks something like this. What have I done? To recap, defined a function, returns option of type I32. It enumerates over all the characters. What does s.chars.enumerate do? It lets you iterate over all the characters. If we ever find the a character, we return not the index. We don't return this. We say, I'm going to return the sum variant with this value. It is similar to me returning a rectangle variant, shape : rectangle, with two numbers inside. That is what this sum of value does. Sum is an enum, and I'm passing in a value inside, so that the final function returns something that whoever called it can pattern match on. I repeat, this function returns an option so that whoever called this function can easily pattern match. कि यार अच्छा, if something was found, then I do this. If nothing was found, then I do this. This is mostly to avoid, null pointer exceptions. What happens in languages like JavaScript is that this can either be one or null. So, you forget to do the null check. You forget to do something like this. If index equal to null, then do the first branch of code. And hence, null pointers or nulls or undefineds in JavaScript can cause a lot of problems, which is why it's formalized like this in the case of Rust. Hopefully, that was easy to digest. Maybe not, let me know. To recap, I've defined a find first function. So I find first a function which returns what? It returns an option of type i32. It returns a number only, but in some cases it will return the actual number. In some cases it will return none. We check if the character is found. If the character is found, then we return the sum variant of the enum. If nothing is found by the end of it, you keep iterating, you find nothing, then we return the none variant, which doesn't need to have a value associated with it. It is none, it doesn't need to have any value associated with it. Finally, we pattern match on the result. If something is found, then we print it. If nothing is found, then we print the letter A is not found in the string. Cool. That is what the option enum does. Next, we look at the result enum, which is very similar, but this one is used for error handling. What was option used for? It was used for null values in Rust. What is result used for? Result is used for error handling. What does it say? The result enum lets you return either OK or error value. The result enum is how you can do error handling in case of Rust. A lot of times a function will either return a value to you or the function will error out. Here I was trying to do something, but that did not happen. I want to throw an error. In case of JavaScript, it happens by throwing a custom error like this. You throw an error in case of JavaScript. In case of Rust, and again in Java, something similar happens, is that your function returns what? It does not return just a number. It returns an enum of type result. I repeat, your function does not return a number. It returns an enum of type result. And this result enum can have two values. I repeat, the result enum can have two variants. The first variant is the OK variant, which means that some value was found, the function worked correctly. The second variant is the error variant or the error variant, which means there was some error which also has a value inside, which is the actual custom error over here. This has the final value. This has the custom error. This variant says कि कुछ value return हुई, the function returned some value correctly. This variant says there was an error that was thrown during the execution of the function. Did not understand? कोई बात नहीं. Let's go through the slides and try to look at an example. What does it say? Write a function that reads the contents of the file. This is a perfect example of a function that may return an error. If this is your Rust code over here, or your .rs file, main.rs, you might try to read the contents of another file, let's say file.txt, but maybe this file doesn't exist. Maybe this file doesn't exist on the operating system. Maybe your main.rs file does not have access to read through this file. And hence, whenever you try to call the function, read underscore file with the path to file.txt, what should this return? What should its return value be? It should be either the text, which is the actual text content, or it should be an error. ERROR. It should either be the text or the error. Why? Because what if the file is not there? If the file is not there, what will you do? Will you crash the program right there? No, your function can just return an error. Here, some error came. I'm throwing the error to you. I am bouncing back the error to you. This is called something in Java. I'm forgetting the name, bubbling the error or something like that, which looks something like this. Let's look at it more practically. This code that you see over here lets you read the contents of a file. The code that is written over here will let you read the contents of a file. I have a main function which does what? It calls fs : read to string. What does it call? It calls this function called read to string on this fs library or this fs. Most probably this is a struct. So on this fs struct over here, which returns you something. Question is, what does it return you? Will it return you text? What is the return type of this read to string function? A function that can either return some string or can error out. If the file doesn't exist, the function should error out. So does this always return you a string? अगर ये फाइल नहीं होगी तो क्या होगा? If this file is not there, will this function panic? Will this stop the program from executing? Or will it just return the error to whoever called it? The better thing to do is just return the error to whoever called it. Okay, you wanted me to read through this file, but this file doesn't exist on the operating system. So I'm just going to give you back an error. I'm not going to give you back a string. I will give you back an error. That is what this line of code does. If you notice the return type of this, let's write this code very soon, but if you will notice the return type of this, it will be of type result. It will be of type result, where result is an enum itself. This is also an enum. It is a custom defined enum. We did not write it like we wrote our rectangle enum, but this enum, already exists in Rust, and you use it to return errors from function. If tomorrow you also want to write a function that returns an error, the result enum is what you should use. Let's try to write this out quickly. Let me delete all the existing code. All right, I've written the code over here. It's less than 10 lines of code. What have I done? Number one, I've imported the read to string function, which comes from the Rust standard library. This is just, a bunch of extra functions that you can import at the top of your file. We'll come to this in the next section where we reach package management. But basically, there are a bunch of functions that you don't have access to by default. The read to string function isn't available globally. Just like, let's say U32 is something that is available globally, or, option is something that is available globally. Read to string is not, which is why you have to import it from a separate library, specifically the file system library over here. And what does this function return? What does it do to begin with? It is a function which takes the file path as an input and reads the contents of that file. As I said, this can be a dangerous task. What if the file does not exist? In this case, what should it return? You might say that it should return an empty string. But what if there is a file that has an empty string? You won't be able to tell, does the file does not exist? Or is there a file with some empty contents inside? You might say, Kirat, -1 it should return. Problem remains the same, right? What if there is a file that has -1 contents in it? How can you clearly tell the result variable, there is an error, bro? Some error came while reading the file. I am going to return you not a string, but a result. What am I returning? I am returning you a result, and then you can pattern match on the result. Result is an enum, pattern match on that enum. If the OK variant is what I returned you, means I'm giving you some data. Feel free to log that data. The file was present, the file was read correctly. If I return you the error variant, it means there was some error. Here are the details of the error. I will shove the details of the error in a value here as well. You can print this to the screen, either this specific error, or you can print your custom error. There was errors while reading the file. So what does the read to string function return you? If I hover over result, what does it say? It says result ka type is capital RESULT. This is the result enum that the Rust library has by default. I can actually take you through its definition, which it'll be a little hard to digest again because it uses generics. But if I remove the generics from here, it looks something like this. It has one variant called OK, which in our case is going to be a string. It is going to either return a string, and it will have an error variant, which doesn't matter. Let's say in our case, that is also a string. The result is an enum, which has two variants. What was rectangle, if you remember? Shape was a enum which had two variants, a rectangle variant, which had two numbers as its values, and then the circle variant, which had one variant as its value, or one value that it needed. This is how we defined our shape enum. This is how the Rust library defines the result enum. They say, if you know you are calling a function that may result in an error, then rather than returning the string, return a result of type string, so that I can either return you an OK variant, everything was fine, or return you an error variant, something went wrong. If you remember from the slides, what did I say? I said result can have two values, either an OK value or an error value. OK means everything was fine. Error means something went wrong. That is exactly what if you look at the result enum, it looks very similar. Of course, there are some more magic over here. If I command Z and show you the original thing, it uses generics. It has this very weird syntax, which don't worry about right now. But hopefully you understand, if there is a function that you call that may return an error, then the return type of it will most probably be null, be a result. You can define your own function as well. What if I define my, oopsie daisy. I define my own function called read from file Kirat. It's a custom function that does the same thing. It takes a file path as an input and it returns the contents of that file path. What will I do here? I can first read the contents. I can be like, okay, this is the result. Now, if I want, okay, I want to return -1 if the file is not found, then I can do something like this. I can pattern match on the result and I can be like, yeah, if everything was fine, then I'm going to return the data. If everything was not fine, I'm going to return, an empty string that says -1. Something like this. Let me change the return type of the function. So this is an ugly implementation of the read from file function. Why is this ugly? This is ugly because it will always return you a string. Read underscore file from Kirat a.txt. This is ugly because it will always return you a string. Even though sometimes the real read to string function will throw an error. If it throws an error, you should not return -1. You should return an error only. You should bubble up the error to the original main function. We are not doing that. Let me run this. When I run this, cargo run, you will see it prints nothing on the screen because I don't print result. So let me print it. It prints -1 on the screen. Do I have an a.txt file? I don't have an a.txt file in my folder. Then why is it printing -1? How will you tell yahan pe ki is there a file over here? What if there is a file that had -1 over here? Then how will you tell ki does the file exist or not? Either be result will be the same. It still prints -1. If there is no file, then also it prints -1. So you are not correctly telling whoever is calling the function what actually happened. If you always want to return primitive types, if you will always return primitive types, if you will be stuck in not using the result enum, what will happen is you will eat up a lot of errors. That is exactly what is happening here. Okay, there is an error that was thrown here, but you ate that error up. You did not bubble up the error to the main function. You thought, ki nahi yaar, I will want to return a string. I will default to -1 as the string, or contents not found as the string. What is the problem here? Okay, what if there is a file that has the same contents inside? You will not be able to differentiate in this result variable. Is there a file that has this content or is there no file currently? Which is why this should return a result of type string. It should return a result. Now, here, what is the syntax? We'll get to, as I said, soon enough. This is generic syntax. It basically tells this result enum mein what should the OK variant return, which I want it to be a string, and what should the our variant return, which also I want it to be a string. That is what this string and this string over here means. But if you don't understand it, it is fine. We'll understand when we reach the generics part. I say my function will return a result now. If I find the correct thing, then I will return the OK variant of a result with the actual data of the file. If I don't find, if the files cannot be read, then I will return the error variant so that whoever is calling me, should be file path, so that whoever is calling me, which in this case is result, whatever, let's say answer, its return type is result of something, or it gets back a result, which could be an error, it could be the final thing. It can easily differentiate by pattern matching again over here on this answer variable. Okay, was an answer returned? Was the file contents read, or was there an error while reading the file contents? Cool. That is why you might want to use the result variant on your defined functions as well, where an error can be thrown rather than actually throwing the error. You can also panic over here if you want. You can stop the thread execution. You can be like, nahi yaar, file not read. And what will happen is, in this case, the program will stop executing right here. That is what happens in most languages, right? You throw an error, and if the error is not caught, the program stops to execute. If I run this, you will see, let me delete the a.txt file. Let me run it again. You will see it says thread main panicked at source/main.rs. The thread itself panicked, the program itself stopped executing. This is another way to do error handling, or throwing errors in a Rust program. But what is the most elegant way? The most elegant way is that you return a result, or you return a result from the function that you know is going to fail. And you know, whoever is calling it can then decide what they have to do with this information. Whoever is calling it can decide that while the contents were being read, the data was read or there was an error. Based on that, you know, whoever called this function can decide what to do next. They can pattern match on the result. That's a better way to do error handling, or you know, the way error handling is done in Rust. Cool. Hopefully that was clear. Let's go back to the slides and see where we are. Let me quickly recap what happens in this function. You first read the contents of a file by calling this function over here. And what does that function do? It returns you a result. Once you have that result, you pattern match on that enum. It is just an enum. It's nothing too complicated. Both option and result are just enums that the Rust standard library has written, and you use them. We pattern match on the result. If everything is fine, then we print the right thing. If there was an error, then we print there was an error while reading the file. That was it for options and enums. We have discussed pattern matching. The next thing is package management, which thankfully is much simpler than everything we have discussed until now. You can add an external crate to your project by running cargo add crate name. Harkirat, what is a crate? Let's discuss this very soon, but high level. This is similar to NPM packages in case of JavaScript. It's external packages that you can bring to your code base. For example, over here, I used an internal package. This read to string function comes from the Rust standard library. You still have to import it at the top, but you know, you can import it directly from the Rust library. You don't have to bring in an external module. But if you remember, initially I said there is this cargo.toml file, which has the dependencies section where you can add a bunch of external dependencies, a bunch of code that other people have written. You can bring that code into your code base. How can you do that? We'll discuss in the next section. All right, let's understand package management next. Usually when you have a project, let's say this is your, you know, main.rs file. A lot of times you want to write a lot of code, but that code is already written by other people. For example, if you want to print the current time in case of Rust, you can write all of the code to use the Rust primitives to write it. Or you can bring in an external dependency, an external library, or more technically what's called an external crate into your project. You bring this crate into your project, and then you can just use the functions that these people have written. You don't have to write all of that logic on your own. This is what is called external packages or external crates. You can bring these external crates to your project to make your life a little bit easier, to reuse a lot of the code that other people have written. If you've ever been in the JavaScript ecosystem, you might have, you might have heard of this library called Express. Express is an external library. You can look at the documentation of Express. How can you use Express on this npm.js page? If you have a Node.js project, you can actually require the code from this Express library. You can bring this Express library to your code base, and you can require code from this Express library. You don't have to write a lot of code. You can depend on that external library. Similarly, in case of Rust, you can bring a bunch of external libraries to your project. Chrono is one such library that lets you do date and time for Rust. If you want to print the current time, the current date, you can use the external library, use high-level functions that they provide you, and just print the current time rather than writing all of that logic yourself. Let's see how that happens for Chrono. If you look at Chrono, the library looks something like this. The way to add that to your code base is by running cargo add Chrono. So whatever is the library that you're adding, cargo add the name of the library will bring that library to your project. Let's do that first. Let me go to my code base here. Let me empty up the thing and let me run the command cargo add Chrono. What will this do? This specific command that I just ran will bring the Chrono external library to my project. If you look at cargo.toml now, you will see it has one dependency that I just added, which is Chrono. So what does this command do? It brings an external module to your code base. Now you can use various functions on that external library. Just like I was using the read to string function, I can use various functions from this Chrono library, whichever function I might need. For example, if you go back to the slides here, the function that we are using over here, or the struct that we're using over here, is this UTC struct. What does the UTC struct do? UTC is a time zone. Everyone follows that time zone. India is in UTC plus 5:30. If you understand this, if not, that's fine. this struct will most probably let me print my current time. This struct will most probably let me print the current UTC time, which is, the central time at some, wherever the sun is in the center, something like that. How do I do that? I first create this now variable, which is by calling this static method on the UTC struct. Most probably this is a struct. This is a static method on the struct, which returns you some struct only is my guess. We can check very soon when we write the code. And then when you write now dot format and a specific format in which you want the date month to be printed, that can, you'll finally get the current time printed in that specific format, the current UTC time. And similarly, when you call local : now, it will print the current local time, which in my case is going to be, India time. So let's see if that actually happens. Let me import chrono UTC or local, and let me try to print the current local time. Let now equal to local now. Current time is now. Why is this cool? This is cool because, all the logic to read the clock from my machine and figure out the current time has been written by these smart folks. I don't have to write this logic. I just bring their code base, their library, their crate into my code base, and I can just use it. I think, as I said, this will probably be a struct. Yes, this is a struct. It is a unit struct, which means it doesn't have, any values associated with it, but it is a struct. It has an implementation below it, and most probably, if I go to the now function, it is just going to be a public function which does not have at self over here, which means it is a static function. You can call it directly on the local struct over here. We've done this syntax before, so hopefully this is straightforward. Okay, we are calling a function which is associated directly with the struct, not with an object of the struct, not with an instance of the struct. We get this variable, we print it over here. Let me see if that does what it's supposed to. If I run cargo run, you will see it prints the current time is this, which is correct in the plus 5:30 time zone, which is, the India time zone. If I use the UTC struct, then, it would print the current time in the UTC time zone, which probably is, 5 hours, 30 minutes behind us. So if I run cargo run now, it gives me, some weird time, 8:50 AM, because India runs 5:30 hours ahead of UTC. Hopefully that's straightforward. How can you bring an external package, cargo, add the name of the project? How can you use that project, start to import things from the project at the top of your file, and then you can finally start to use the functions from that external module. Why would you want to do this? So that, you don't have to write all of the code. You depend on external libraries to, write most of the code. You just stitch them together. That's what most end user applications are, right? Whenever you're creating a MERN stack application, you're depending on the Express module package. Similarly, when we create a backend application over here, you will see we will depend on some external crates that, will provide us some functions that we will use to finally write our application. Cool. We're done with the very first part over here, which is the easy bits of Rust. That itself took 1.5 hours. I'm super surprised. And I think this is really slow. Let's get into some hard bits from part one. This should probably, hopefully not take more than 30 minutes, but I could be wrong. Then we will get to the actual gist for today. Let's understand memory management in Rust, mutability, heaps versus stacks, ownership, borrowing, and references. Let's get into that next. Alrighty, getting into some slightly advanced concepts. I wouldn't call them advanced. It's just Rust does things a little weird, which is why, these get a little confusing. So the earlier you understand these, the better. Again, we've covered this in a 4-hour video, so you can go there. I chose some very raunchy examples over there. I'm going to keep it simple here. We're going to understand memory management, mutability, heaps versus stacks, ownership, borrowing, and references. The last three are what are going to boggle your head a little. The first three are not too difficult, and if you're coming from a C++ background, you've probably heard of them before. Without any further ado, let's understand memory management in Rust. And before that, what exactly is memory? What do I mean when I say memory? When you buy a machine, if this is my Mac machine over here, what all components does it have? It has a CPU, it has a GPU, and it has something called the random access memory. You might have in school heard that this RAM is temporary storage or temporary memory, and the SSD is the hard drive, that is the actual persistent memory. So what exactly is this memory supposed to do? Have you ever guessed? Why do people optimize to get this to be, 64 GB or 128 GB? Why do people pay more and more money to increase the amount of RAM that they have? And the answer is because whenever you run a program, for example, when I'm running this Rust program by running cargo run on my machine, I'm taking up some space on this memory. This memory is really small compared to your hard drive. Hard drives are 1 TB, 2 TB. This memory is small because this is really expensive. Any chip over here, the smallest single byte over here is very expensive for you to buy and run, which is why this is only used for the programs that are currently executing on your machine. For example, if on my machine I have Google Chrome running, then Google Chrome is taking some memory over here. If I have VS Code running, VS Code is taking some memory over here. If I have some Node.js program running, the Node.js program is taking some memory over here. When the program executes, the variables of that specific process are stored here in memory. That is what memory management generally means. Your laptop or your machine is eventually going to have thousands of these softwares that are running. For example, I'm running OBS, I might be running Zoom, I might be running Edge, Chrome browser, Terminal, Premiere Pro. All of these are softwares, all of these are programs, processes that are running. They take up some space in my memory. For example, if I open Premiere Pro over here really quickly for you, you will notice that Premiere Pro has a bunch of files. Some of these files are loaded in memory right now. Some of these aren't, it's probably a bad example, but a better example probably is, Google Chrome, I'm on this specific tab. I see the tab written over here. I see all these contents. They're stored somewhere in memory. That is why I see them over here. So memory is a very scarce resource on a machine. Whenever you're running any Rust project, it is taking up some memory in your RAM. If your RAM is 16 GB, some, let's say 2 MB, 5 MB, 10 MB are taken by your Rust program. If your Rust program has a lot of memory, let's say it, defines a vector that has a length of 10 is per 10, then of course it will take much more memory over here. If it just defines two variables, then it will take much lesser memory. Cool. How much space do you think a program actually needs? If you run a Rust program, do you upfront tell memory, I need 10 GB of space. I need 1 GB amongst this 10 GB. Do you dynamically allocate or deallocate memory in this, RAM over here? And the answer is both. You do allocate some static memory. I need this much memory. You also allocate a bunch of dynamic memory. There's this concept that you might have heard of, which is called heaps and stacks, that we will be learning about very soon. But when a program runs, it does reserve some memory. I'm going to run my program. This much memory I need over here, some static memory. And it also reserves it doesn't reserve some dynamic memory. It can ask for more memory. I need more space. I need more space. I need more space. It can request the operating system for more space. If the operating system obliges, then you can, get more space for your program. If let's say your program, keeps pushing elements to an array, then you will need more space. So you keep asking the operating system for more space. If you look at this program, I define one variable i32, another variable i32, a third variable which is also i32, sum of these two. I print the sum. What do you think? How much memory roughly should this program take? Well, we need one i32 number, which means I need a 32-bit number over here. That will probably be stored over here. That is what 32 over here means, right? It means it's a 32-bit number, which means I need 32 bits of space in memory for this first variable. The second variable, how much will it take? It will also take 32 bits. The third variable, how much will it take? Since that is also the sum of two variables, it's a fresh variable, the third variable, that will also take 32 bits. So how much space does this program need? Roughly 96 bits. There is some extra space that comes with, these function calls. But ignoring that, you can say, we have defined three variables. This is the amount of memory we need over here. Why are we discussing this so much? Because Rust shines when it comes to dynamic memory allocation, and more specifically, it shines when it comes to memory management, which is why we're spending time here. We wouldn't even spend this time on a language like JavaScript or Python, but on a language like Rust, the whole, premise of Rust is, it lets you do create very safe programs. We'll come to what safety means, which is why we're, spending our time over here trying to understand how much memory does a program take. Here is a better example. What did I say? There is some static memory that you store. There is some dynamic memory that you store. Whenever you create a Rust program, similar logic applies to C++ as well. There are two sort of memories that you have, the stack and the heap. The stack is where you put static data, the data that you know iska size is going to be this much. If you can predict the size of a variable at compile time, I repeat, whenever I run cargo run on my machine, my .rs file first gets converted into a binary, and then this binary is what eventually runs on my machine. Okay, there are two steps to running any Rust program, any C++ program. The first step is compilation. The second step is actually running it. So if I can predict the size of something during compilation, I repeat, if this is a main.rs file, during compilation, I can predict, ये तो 32-bit ही होगा. This cannot be increase or decrease in size. Neither can this increase or decrease in size. These are static when it comes to the memory that they take. They don't take more than 32 bits. They will never take more than 32 bits. But can I say the same for a string? A string can initially be Harkirat, which means it only needs, let's say, some random number, 200 bytes. But eventually I could add more things over here. I could make it Harkirat sing. Then I would need 200 plus 100 equal to 300 bytes. I might increase the size of a variable. I might decrease the size of a variable. You might say, Harkirat, wo to I can do for the number as well. You might say, I can do that for the number as well, Harkirat. I can increase the value of this number. If this number is initially 1, I will, take this number a equal to 1, and then I will make it a equal to 100. Does that mean I had to take more space over here now that I have a bigger number? The answer is no. When you create a 32-bit number, when you write const or let a equal to u32, you are reserving 32 bits in memory for it. You are saying, 32 bits belong to me. Assume this is 32 bits that I have mentioned over here. Now, if you want to store 100, or very small number like 1, then most of the bits here will be 0. And the very last bit here, let's say, will be 1. If you want to store a bigger number here, let's say 1000, then maybe these all bits will be used. If you want to store 10 raised per 5, then maybe these all bits will be used. If you want to use 10 raised per 8, then maybe all of these bits will be used. So these bits are reserved. When you create a 32-bit number, you reserve 32 bits. If it is a small number, it will not use all the 32 bits. If it is a big number, it will use all the 32 bits. So the amount of space that a number takes does not change as time goes by, as your program actually runs. But the amount of space that a string takes does change as time goes by, which is why for a number, it will look something like this. And I'm going to introduce some more operating system jargon over here, which don't worry too much about. But whenever you define a function on this stack. The name itself is stack. Little bit of DSA people understand stack. On this stack, I push the main function ka what's called stack frame. The thing that you see over here is the frame that stores the main function ke variables. The main function has variable 1, variable 2, variable 3. All three of these are stored on the main function ka stack frame. If I had more functions and more function calls, we will see how the stack changes. But for this very simple program, this is what memory would actually look like. You would have a single stack frame for the main function. You will have 3 variables that you've put over here. And when the program executes, this is the amount of memory that you're taking. That's 32 plus 32 plus 32, 96. When the program executes and ends, then this memory is eventually freed. That is how you would describe the memory of this program. But what do you think happens here? I now have a main function which defines 3 variables, but the third variable comes by calling another function called find_sum. Calls another function find_sum, which takes 2 inputs a and b, which are both numbers, defines a third number, answer, and then returns the answer from here. How do you think memory changes over here? Initially, when the main function is called, the main function is what gets put onto the stack. The very first stack frame is of the main function. And how much space does it take? It takes 96 bits of space because we want to define 3 numbers here eventually. Then the first variable gets stored, let's say over here. The second variable gets stored, let's say over here. The third variable, before it is stored, what happens? This function gets called. And what did I say? When you call more functions, they get pushed onto the stack. We push this function call onto the stack. We create a new stack frame for the find_sum function call. And how much memory does this guy need? it has a variable A it needs to store, it has a variable B it needs to store, it has a variable answer it needs to store. So memory would look something like this. After this function is actually called, you would have another stack frame which would have these 3 variables. It would do its thing over here, add those numbers, delete those numbers, multiply those numbers. And then eventually after this line of code runs and the function gets returned, the stack frame gets popped off the stack. After the function finishes to execute, this memory gets freed. You don't need the A, B and answer variable that were here anymore. This function was called, this function completed its execution, it can be popped off the stack frame. And now you're back to square one. You're back in this function. You have this memory for it. You have 96 bits of memory that your program is using right now. How much was your program using here? 96 into 2. It needed 96 bits over here, 96 bits over here. How much does it need here? Just 96 bits. You finally print the thing, you're good to go. Program exits, this gets popped off as well. Your memory is freed. That is how memory gets allocated for simple data structures. For data structures like numbers, memory management is something you don't have to worry about. Define your variables, use your variables, does not matter. Rust, whenever you're writing Rust code, you will not feel any different from JavaScript, Python or Java until you are writing things like these numbers. When you're dealing with non-dynamic variables, variables that don't change at runtime, whose size cannot change. The size of this number will never change. It will be 32 bits always during the execution of this function. Versus that is not true for strings. So let's understand. Okay, until now we have only stored things on the stack. Let's try to store things on the heap next. When do we store data on the heap? And why is this so difficult, weird? When you're writing Rust code, as soon as you start to store code over here or store data over here, why do things get complicated? What is the difference between heap and stack? Let's understand that next. In the slides, this might be a little flipped. In the slides, I think I wrote stack over here, heap over here. So I've just corrected that over here. These are all the properties of the heap. These are all the properties of the stack. The heap is dynamically allocated at runtime. What does that mean? Okay, whenever you put memory over here, it comes in dynamically. You put a string here dynamically when the code is running. And then let's say you add something to the string, you dynamically add more things in memory over here in the heap. Then you delete something from the string, then this area gets removed. So you dynamically allocate data on the heap as your program executes. Versus here you saw here whenever a function runs, we statically say कि 96 bits are stored over here. Another function ran, 96 bits are stored over here, so on and so forth. Dynamic allocated at runtime, static allocated at compile time. Basically means whenever you are compiling your code, the Rust compiler knows कि यार ये जो main function है, this main function needs 96 bits. This one needs 96 bits. Versus it cannot predict when you're writing strings what the size of string needs to be and how much data it needs to reserve over here. Heap is much larger in size. Strings are much larger. You can have a very long name versus numbers are just 32 bits and smaller in size. This is one of the reasons that heap is dynamically allocated, because when you have a lot of data, you cannot store it on the stack. You'll run out of memory. Versus heap, you have you can ask the operating system for as much memory as you want. So large data usually stored on the heap, small data stored on the stack. Slower due to dynamic allocation and deallocation. This means, what does dynamic allocation and deallocation mean? Okay, when your program is executing, when you reach this line of code, you dynamically ask, give me more space here. Someone pushed sing to the last name variable. Initially the variable was just Harkirat, but sing got pushed to the end of the string. So you need more space over here. Hence, it takes more time for you to ask the operating system for more space, more memory, and hence storing data on the heap is slower, storing data on the stack is faster. Used for dynamic data or large data, things like vectors, hash maps, or strings. Used for small data, fixed size variables, and function call information. Usually used for things like numbers, booleans, that whose size is fixed. Used for things like strings, vectors, hash maps, whose size you cannot predict until the program actually runs. Until the program runs, you don't know how much data you will shove into a string, a vector, or a hash map. So you cannot judge how much memory you need over here at compile time. Versus anytime you're writing numbers, it'll only take 32 bits. So you can predict the size of every stack frame upfront. That is the difference between heap and a stack. The things that are usually stored on the stack are numbers, booleans, fixed size arrays that are not going to change in size, structs, structs that don't, have a string as the type. If they have a string as the type, then of course the underlying string will again be stored on the heap. Let's not go there. A struct that looks like this, which has just numbers or just primitives, will also be stored on the stack. And references, which we'll come to what these are very soon. Stored on the heap: strings, vectors, hash maps, large arrays, and structs that cannot fill in the stack. So the first three are things that dynamically change as your program runs. As your program runs, your logic might change a variable, let's say where name or whatever, let name, it starts with Harkirat and then it gets changed to Harkirat Singh. Then it gets changed to Harkirat Singh Kamboj. Then let's say Singh gets removed, Harkirat Kamboj. Its value changes as time goes by. So, strings, vectors, and hash maps are data structures like this. Harkirat, what are vectors and hash maps? We'll discuss in the advanced part today. But strings, hopefully you understand their size changes, which is why they're stored on the heap. Large arrays, there are some, as I said, the amount of data that you have on the stack is limited. So if you have some data that is very big in size, even if it can be stored on the stack, it is usually stored on the heap. Cool. Let's understand how would memory management happen over here. What would the stack and the heap look like if you now use a string? I'm not using a number, I'm using a string. Let's see how this hello, all of this data is stored. Does it stored here or is it stored here? If it is stored here, is there something corresponding that is stored here as well? Let's see. When you define the string, you store this string variable, this name variable on the stack. But this doesn't hold all of this value. ये जो hello value है, all of the contents of the string are not put on the stack because you cannot predict how long the string would be eventually. Right now it is 5 letters, it is fine, you can predict. But as your program executes, if you have, a for loop over here, then you don't know what this for loop will do. It might send out a network request. God knows what response comes from there. You can't upfront predict the size of the string will become smaller or bigger. So you cannot store this string, the final contents of the string over here. You can try, but what will happen is if this becomes really long, eventually you'll shove out of this stack. You cannot. The size of every stack frame is fixed and defined upfront. So this actual content is stored on the heap. But what is stored on the stack? A reference to this specific pointer, an address of this specific pointer. If you have a 32-bit machine, then you can find the address of this specific H, the first H, the first letter where you have stored something. You can store this address in just 32 bits. What is actually stored over here on the stack is the address of this specific thing. And something that points to this H, and then after H, E comes, L comes, L comes, and O comes. You can find the rest of the content on the heap. What is stored on the stack? The actual variable. Why do you do this? Because you don't know if this becomes hello world in the future. If it does become hello world, you can ask for more dynamic data on the heap. What did we say when we asked about the difference between heaps and a stack? We said dynamically allocated at runtime. The heap can be allocated at runtime, which means if you change the length of this variable, hello becomes hello world, you can dynamically ask for more memory on the heap. You cannot do that on the stack. Cool. That is how you store strings, even arrays and vectors. Not arrays and vectors are also stored here. Fixed size arrays, an array that whose size you won't change during runtime, they can be stored here. But everything else, hash maps, vectors, an array of characters, which is effectively a string, is always stored on the heap. Anything that changes during runtime is what's stored on the heap, but you always have a pointer to that from the stack. So what does the stack hold? It holds this variable. What does the heap hold? It holds this actual content. The content goes here, the variable goes over here. Cool. Why are strings stored on the heap? Because they are large and their size can change at runtime, and the size of the stack frame needs to be fixed. First reason you can actually ignore. The second is the bigger reason. Okay, their size can change at runtime. You don't know if a string, becomes longer or shorter, which is why, it needs to be stored in a place where you can ask for dynamic memory. You cannot do that on the stack. You can do that on the heap, which is why it is stored on the heap. Do we understand memory management, heap versus stack? We haven't really covered memory management. We've just understood memory. What is memory? And then we've understood the difference between heap and the stack. Next up, we're going to understand mutability, which we already have, which is a very simple concept. So I'm not going to spend too much time here. Basically, whenever you define a variable, for example, let name equal to string : from hello. I've defined this string. If I try to add something to the end of the string, let's say the string was originally hello, I tried to add world to the end of it. This code will begin to complain. It will give you an error. Why? Because all variables in Rust by default are immutable. What does immutable mean? It means you cannot change their value. But if you want to make them mutable, you can add the mute keyword over here, right? When you define the variable, add the mute keyword, that will make it mutable. And now if you have hello as the original world, you can push a string to it like world. Now you have a longer string. You might ask, Akirat, why is this stored on the heap? You can clearly at compile time check here hello is the first word, world is the second word. It would need, let's say, 200 bytes on the stack. Why are we not storing this string on the stack? Because you don't know कि इसके बाद if a for loop comes, the compiler cannot just be like, अच्छा, over here तो I can almost say that the string is constant. You can actually say that. You can say, the string will eventually hold this contents, hello, world. The compiler can sort of, let's say, infer that. So you might think, Kirat, why don't we store this on the stack? Because, you can have conditional logic in a compiler, but, Rust doesn't. It says, kya string banai hai? We know string can be highly dynamic in nature. Just because over here you are not adding random things to it, removing random things from it, doesn't mean, it won't happen eventually in a for loop, let's say. And hence, the Rust compiler always stores strings on the heap. And, irrespective of if this is very simple logic, the compiler isn't able to infer, the size is going to be, let's say, 200 bits and store it on the heap. It'll always store it on the stack. Cool. That covers mutability. What do we learn in mutability? If you define a variable, it needs to be mutable if you want to change its value. That is true for strings as well as numbers. Let me quickly code this out and show you if you'd like to, see this in action. If I define a variable like a simple number also, let a equal to 1, and I'm trying to change its value. As you can already see, there's a red squiggly up there on the line in which I try to change its value. What does it say? Cannot mutate immutable variable A. Every variable is immutable by default. If you want to make it mutable, if you want to allow changing its value, you make it mutable like this. Cool. Hopefully that's clear. That's it. That's all we had for mutability. Next up is when we get into some slightly more hard concepts. Ownership, borrowing, and references. One more thing, I think. Ownership, moving, borrowing, and references. Our longer video, 4-hour video, covers this with some very weird examples. You can go there. I'm going to cover it here fairly simply. What are these 4 things, and why do they become important in the context of Rust? These are also only Rust specific things. Everything we saw until now is, you'll see it in other languages. You'll see package management in other languages. You will see ID setup in other languages. You will understand how to initialize a project, functions, structure exist in C++, enums exist in JavaScript, option and result exist in Java, pattern matching is again Rust specific, package management exists everywhere. These 3 things, or more specifically, these 4 things are highly Rust specific. So you need to understand them quick if you want to get into this language. So let's understand what is ownership, moving, borrowing, and references next. All right. Why are we learning these 4 concepts? Because Rust does memory management a certain way. There are high level 3 ways languages do memory management. It is number 1, by using a garbage collector. This basically means, firstly, what does memory management means? It means cleaning things up from the heap. Whenever you define a variable, like hello on the heap, you allocate this memory. Deallocating that memory, removing that from the memory whenever this name variable goes out of scope, is high level what we mean when we say memory management right now. When we say memory management, we mean when you are allocating data on the heap, where all are you putting data? When that variable goes out of scope, are you removing data from that specific spot or not? That is what it means when I say allocating and deallocating memory, or memory management right now. And as the name suggests over here in the first section, garbage collector, which means whatever things are no longer needed on the heap, removing them from there. That is the first way to do memory management. A lot of languages do this. This is why you don't have to worry about memory management in Java or JavaScript, because they have the concept of a garbage collector. They have something running in the background that keeps on checking, okay, this is the heap. What all data over here is not needed anymore. It removes that data from the heap. Usually written by smart people, usually no dangling pointers or memory issues. You can't do manual memory management, and examples are Java and JavaScript. Let's go over all of these topics really quickly, all of these points. Written by smart people, the garbage collector that we're talking about is usually written by really smart people, because any optimization you can do there will make the programming language really fast, or relatively fast. So memory or garbage collectors are written by some really smart people. They usually don't run into memory issues. What is a memory issue? You might have heard of this thing called a dangling pointer. If not, can you guess what a dangling pointer is? If I have some variable on the stack which points to some memory on the heap where no data exists, that is a pointer that is dangling. It is pointing to a random variable over here on the heap, which is why it's a dangling pointer. This is one of many memory issues that you might run into. You might have heard of oopsie daisy. You might have heard of what do you call it? Buffer overflows. You might have heard of buffer overflows. You might have heard of double free errors if you've heard of them. These are like various like memory issues that happen that don't happen in Rust, or will not happen in Rust 99.9% of the time because of concepts like these. Can they happen in this specific set of languages, Harkirat? The answer is no here also, because as I said, some really smart people have written the garbage collectors. So usually no dangling pointers or memory issues. You can't do manual memory management. Harkirat, what is manual memory management? Putting things over here, asking for some memory on the heap, asking to increase the memory on the heap, allocating memory, deallocating memory. You can't do that. These languages are one level up. That is why they say Rust is a lower level language. C is a lower level language, because you can access the memory, you can shove bytes in there. You can't really do that in JavaScript. Most applications don't require you to have extremely low level language, which is why most programs are written in JavaScript. But Rust, provides you that only. C, C++, Rust let you do manual memory management. So first is garbage collector. We're not learning that. Manual memory management. What is this? Okay, you allocate and deallocate memory yourself. The developer writes the logic to put data in here and remove data from here, read data from here. It can lead to dangling pointers and memory issues. The biggest problem with the second way to do memory management is you as the developer get power to allocate memory and deallocate memory on the heap, but developers are dumb, and you might write wrong code that has a pointer to a null reference, has a null pointer that tries to free some memory that you took twice, a double free error. So these are common errors, common memory issues that come with a C or a C++ program, which is why Rust solves it a third way. What is the problem with doing memory management the way C does? Manual memory management. We will see this example very soon. That is why this is marked in red over here. I'll show you an example in the next slide where you will clearly see there is not a dangling reference. We basically forget to deallocate memory. You'll see in the next slide a very common memory issue that will happen if you're ever writing C++ code as a beginner, but you can't do the same in Rust. Rust will force you to avoid those errors. I repeat, think of Rust as, the people who wrote Rust said, C is a great language, but developers are dumb. So we are going to force developers to write code a certain way so that they cannot land into a situation where they run into memory issues. I should write that down. Wow, that's quite a statement. Rust, you get the idea. I'll probably just put it on the screen. Rust was written by developers that said C is great. You do need sort of manual memory management. That is not bad. But since developers are dumb, we are going to force developers to write code a certain way so they don't run into memory issues. Let's see this with an example. Let's see how does C do it? Why is there an error? How does Rust do it? And why is it better? When it comes to memory management, why does it lead to less memory issues? This C++ code that you see on the right has a memory leak. What do I mean by a memory leak? I mean, it has a function over here called create string, and whenever this specific program will be called, first we will put main on the stack, then we will put the other function on the stack, and we will manually allocate memory. What are we doing inside this function? If you look at it, I am manually allocating memory over here. I am creating a new array with 30 bits, I would assume, I could be wrong, or probably 30 bytes. I'm probably allocating 30 bytes on the stack. I am dynamically allocating memory here on the stack. I'm taking 30 bytes on the stack to store my string over there. Even in case of C++, if you want to create or put dynamic data like a string or a vector on a C++ program, it will be, you will ask the compiler will ask the OS for some extra space on the heap. You will store the data over there. You print the string, but you forget to deallocate memory. If you look at it, I have commented this line of code that should have been there. What does this line of code do? This line of code would have removed this from the heap. I did not remove this from the heap, which is why, what is this? This is a memory leak. Our program will execute, and finally we will be returned to the main function. This will get removed from the stack. The second frame will get removed from the stack, but we will still have memory over here. We will still have memory allocated, which is why this is a memory leak. And developers can write this code from time to time. You do write this code. There is this very common pattern which you can read about, RAII pattern, which is sort of what Rust ends up doing under the hood. I'm not going there, but you should read about it if you want to read something extra. But C tried to solve this problem by introducing the RAII pattern, which would sort of force the developer to clean up memory. But again, this isn't something you can force in C++. You can just hope that the developers follow the RAII, resource allocation something, I forgot the name, pattern to clean up memory from correctly. That is not happening in this code. You write very basic C code over here, 25 lines of code. You leave out a very basic memory leak. Okay, when you defined a function and you allocated some memory over there, you should be deallocating that memory over here, right? You are not returning this stir to the original function. This stir will no longer be valid. It goes out of scope. So why are we storing some data on the heap over here for this stir? When we know it has gone out of scope, it cannot be used in the main function. When the scope of this function ends, when the scope of this stir variable ends, this data should be cleaned up so that there is no memory leak. Does not happen in C++ unless you manually delete the data, you manually deallocate the data. This is a very common example of a memory leak. What did we say happens in C++? Okay, can lead to a bunch of memory issues because you allocate and deallocate memory yourself. The developer does that yourself. That is exactly what I'm doing here. Since I forget to deallocate memory, I run into a memory issue. C++ code has a memory issue. When you run this main code, you call the create string function. This is what the stack and the heap looks like. I've not written the stack correctly here, but you get the idea. As soon as I create some new data and try to copy it over the heap has this, hello from heap memory leak variable stored over here. All of this string, all of this data, all of these characters are stored on the heap over here. And then finally, when I come back to the main function, the data is still alive on the heap, even though there is no references to the string. There is no variable on the stack that is pointing here. When you come back here, there is no variable called str over here. There is nothing pointing to this data, but you haven't cleaned up that data, and hence this is a memory leak. Now let's get to the Rust way of doing memory management, which will take this problem away. As I said, it will force developers to write code a certain way so that they cannot run into this issue. And whenever a variable goes out of scope, it will automatically be deallocated. You don't have to manually deallocate it. What is the third way to do memory management? First way is garbage collection. Second way is manual. Third way is the Rust way. Rust has its own ownership model for memory management. It makes it extremely safe to memory errors. Errors like these that you were able to do as a developer in C, you can't do unless you're writing unsafe Rust. You cannot do these errors. The compilation itself will fail. The compiler will tell you, okay, you are trying to do something which may lead to a memory issue, so I will not let you do it. Let's look at the Rust way. Do you think there is a memory leak in the code that you see on screen? It looks very similar to the C++ code we had written. There is a main function over here which calls a create string function, which defines a string and then prints it on screen. That's it. Do you think when this string gets allocated on the heap, does it get deallocated at this point or not? What would the memory flow look like for this application? Initially, main gets pushed onto the stack, then create string function gets called, then create string gets pushed onto the stack, where we have a 32-bit variable which points to this hello, 5 contiguous set of bytes in memory which have HELLO stored over there. What happens when this function ends? This will get popped off, but does this get cleared off the heap as well? The stack frame definitely gets popped off, but does the heap clean up itself? The answer is yes. Rust handles cleaning it up. Question is how? Does Rust have a garbage collector? How does Rust know that this is the right time for me to clean up the S variable? And the answer is by using something called ownership rules. Rust says that I'm going to follow these ownership rules for memory management. It says, keep this working through the example. This comes from the Rust book, which is why it's taken from there. So this first statement doesn't make too much sense. But what does it say? It says each value in Rust has an owner. Specifically, anything that you're storing on the heap over here has an owner. And what is the owner? It is this variable right here. They say there is something on the stack which will own this data on the heap. And whenever this variable goes out of scope, Rust will clean up the corresponding data on the heap as well. Rust says that unlike C, where we expect the users to deallocate memory, the developer needs to deallocate memory, Rust says that whenever you put something on the heap, I'm going to assign it an owner. And when this owner goes out of scope, it probably makes sense for this data to get removed as well. And hence, the ownership rule says each value in Rust has an owner. There can only be one owner at a time. You cannot have multiple owners. This is what leads to double free errors. If you have two things that are trying to clear something on the stack, that leads to double free errors, which means you're trying to free the same address twice, which might have been taken by some other program. So every value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Whenever the owner goes out of scope, this is the owner of this data on the heap. The S is the owner of the value hello. Whenever S goes out of scope, which happens over here, what does going out of scope mean? Here, whatever braces it was inside, those braces have ended. Whenever this function ends, control reaches here, the function has ended, which means S goes out of scope. If S goes out of scope, it means you can clean up the data from the heap. So that is what ownership is in Rust. Ownership in Rust says that whenever you have data you're storing on the heap, there will be one owner of that data. And whenever that owner goes out of scope, I will clean up the data on the heap as well. You can clearly see this goes away. This takes away the problem that the C++ code had. Our C++ code had a memory leak. This code will not have a memory leak. Why? Because as soon as S goes out of scope over here, the data gets cleaned from the heap. This is very similar to garbage collection only. Garbage collection and how Rust is doing the Rust way are very similar. Only when a garbage collector works in a language like JavaScript, it periodically from time to time figures out nothing is pointing to this variable. S has gone out of scope. Let me clean this up. Versus in case of Rust, whenever S goes out of scope over here, Rust will clean up the data from the heap as well. So it's like a very mild difference. But the good thing is, since Rust doesn't need a garbage collector running in the background, constantly checking, is there some data that is leaking? Is there some data that is leaking? It is much faster than a language like JavaScript because it doesn't have a garbage collector that is interrupting, the control flow from time to time, figuring out what needs to be cleaned up and cleaning it up. In case of Rust, whenever a variable is going out of scope, we are cleaning its corresponding data from the heap. It's as simple as that. That is how Rust does memory management. Why is this cool? This is cool because the way ownership works, we will see this very soon. It's very hard for you to run into memory issues. Rust is preventing you from running into memory issues upfront. Let's see how. Let's understand the concept of moving a variable next, which is one of the reasons that, Rust is memory safe, and how does it, achieve memory safety in one more scenario. Let's look at that scenario. Let's look at the code that is written over here. We have a main function which calls a function called create string. Here, I first define the s1 variable. I define the string s1. Then I define another string s2 and I say s2 is equal to s1. What do you think happens over here? Can you guess? There are like various things that can happen when you say let s2 equal to s1. Does s1 get copied? Do you create a fresh variable? Something similar to this over here. Do you have another string created in memory? Maybe. Is this s2 pointing to the same thing? Do you sort of have a reference here, or does something else happens? Let's see. Let me tell you up front, this code doesn't even compile. If you look at it, there is a red squiggly over here. Whenever you try to assign a string to, let's say, a variable s1, and then you say let s2 equal to s1, if you try to use s1 after this, I repeat, after this line of code, if you try to use s1, it will give you an error. Let's look at what that error is, and that will probably give you a better idea of what I mean when I say moving a variable. Let's see this in action. I define a variable, a string, let a equal to and then I say let a2 equal to a1. Simply do this. Right now, if I print a2, no error appears. If I run this, everything is good. This is a normal program. But when I try to use a1, you will see a compilation error. What does it say? It says borrow of a moved value a1. It says you are trying to borrow a value. Now we'll get to what borrowing is and why does it say that you're trying to borrow a value here. That's because the println macro, borrows the value. Don't worry about that. But what is the second part here? Borrow of moved value a1. What were we learning in this section? We were learning about moving. The second thing, we have understood ownership. We're understanding about moving. What does the code say? The code says, or the error says, you are trying to borrow a moved value. a1 gets moved over to a2. After you do this, let a2 equal to a1, you are not cloning the a1 string. You are not creating another variable here that looks similar. No. You can also do the same thing by doing a1.clone. If you do a1.clone, then it's a different thing. Then in memory, you have created a new variable. You have two different variables in memory, one a1, one a2. Then feel free to use a1, feel free to use a2. Nothing is wrong. In fact, when you will be writing Rust code for the first time, you will add clones everywhere. You will see an error like this. You will say let a2 equal to a1. You will try to use a1. It will give you an error. You will just clone it. You will move on. That is how a lot of times you write Rust code initially is just copy everything, over and over. But this is bad. Why do you want to store Harkirat in two different places? You should just store it in one place in memory. If you try to do that, you see that a1 becomes invalid. Why does that happen? Can you guess? We learned about ownership before this. What did ownership say? It said only one owner at a time. It said if you have some value on the stack, which in this case is, if you have some value on the heap, it can only have one owner. Right now, a1 is the owner. When you do this, the owner gets moved. This string ka owner now becomes a2 and a1 becomes completely invalid. This string is now owned by a2. a1 is completely invalid. You cannot use a1 after this. Why? Because I kept on saying, right? Rust forces you to write code in a way that you cannot have memory issues. If Rust did not do this, it did not, have this concept that only one owner can be at a time of a specific value on the heap. Then what would happen is whenever a2 goes out of scope, you would try to remove the data from the heap. And a1 would still be pointing to that data. You would have a dangling pointer. Or if you try to free it again, whenever a1 goes out of scope, you will be freeing the same thing twice from memory. That will be a double free error. So as you can see that Rust makes it very hard to write code, which is exactly what is happening here. You would expect these two lines of code, or these 4 lines of code, to just run in any other language. If in any other language you write let string1 equal to Harkirat, let string2 equal to string1, and try to print string1 and string2. Some languages might, copy over the string, so you have two places in memory where Hakirat is stored. Some might use a reference. Okay, both of them are pointing to the same memory. But what does Rust do? Rust invalidates the first variable. It says ये तो valid ही नहीं है. Why? Because it wants to follow a clear ownership rule. Okay, only one person will own the value. If at this line of code you think A1 needs to be moved over to A2, okay, you can move it. But A1 is no longer valid. I will not allow you to use A1 ever again, because if I allow you to use A1, then if you try to do something like this, okay, you define A2 over here. Okay, this code is valid. There's nothing invalid in this code. I just reduced the scope of the A2 variable. I said यार A2 को यहीं define करो between this scope. If Rust did not have strict ownership rules, if Rust did not say that this value can only be owned by one thing, if Rust did not make this variable invalid, what would happen? When you run this line of code, Harkirat gets put on the heap. When you run this line of code, A2 becomes the owner of that specific value. Let's say there are multiple owners. A1 is also an owner. A2 is also an owner now. Whenever the scope ends, it will try to clear data from the heap, and over here you will be referencing a null pointer, a dangling pointer. That is why you don't want to, that is why you are forced to write code this way. That is why, the ownership rule sort of kicks you in the butt over here whenever you try to write this code, because Rust wants to be safe upfront. It says, we want memory to be extremely clean. We want to avoid all double free errors, all dangling pointers. And hence we have this ownership rule. If you want to oblige, if you do want to do this, Rust says, okay, bhai, I will give you a compilation error. If you try to run this, you'll see a compilation error. Fix it. Clone the string. Do something better. If you want to have two owners, okay, create two different places in memory where you store this data. I will not let you point two variables to the same thing. I will not let two variables point to the same variable. That is what the Rust ownership rule force. Why do they force it? For memory safety. To recap, if this is the heap and this is the stack, there is always a single variable that owns a value on the heap. If you try to assign S2 equal to S1, this variable becomes the owner and the first variable becomes invalid. It's almost like that variable isn't defined anymore. You cannot use that variable, so that whenever S2 goes out of scope now, then this memory can be cleaned, but only one owner at a time. Let's see this once more pictorically. What do you think happens when you do this? Do you think A happens or B happens? I have two options over here. When you write this code where you say let S1 equal to string.from hello, then to chalo this happens. S1 starts to point to something on the heap. This over here is the heap. This over here is the stack. Again, this over here is the stack. This over here is the heap. Do you think case 1 happens or case 2 happens? Case 1 says, here when you do let S2 equal to S1, we copy over the string. We have two separate places on the heap where we are storing the string. This one points to the first one. This one points to the second one. Does this happen? No, this does not happen. You don't by default clone the string. If you want, you can call a1.clone and then yes, this would happen. If you clone the original string, this would happen. But if you simply say let S2 equal to S1, then this though doesn't happen. Does this happen? Do both of them point to the same thing? The answer is no. Why? Because if this is the owner of this and this is the owner of this, then as soon as one of them goes out of scope, the ownership rules will clear this as well. The ownership rules say if the owner goes out of scope, value goes out of scope as well. And you will have a dangling pointer over here pointing to some data that has been deallocated. And hence, what is the right way to do this? What is the right way to visualize ownership? It is, okay, initially S1 was pointing here, that is fine. As soon as this line of code ran, then S2 is the owner of this guy. S1 is no longer valid. That is what this gray section over here means. Okay, S1 you cannot use after this. If you try to use it, the Rust compiler will begin to complain. That is what we mean when we say moving a variable. We are moving the S1 variable over to S2 over here. If you remember the error, it said borrow of a moved value. It is clearly telling you here S1 has been moved over to S2, so you cannot use it anymore. And this is one example of movement. Here is another example where exactly the same thing happens. Even though it doesn't look like it, the exact same thing happens. Let's say we had the create string function. Here I defined the string s1, and rather than doing let s2 equal to s1 over here, I've changed this line of code. I have not done let s2 equal to s1. I have called another function called print underscore str, where I am passing s1. I am taking this s1, passing over here. This is equivalent to me doing let s2 equal to s1. Me passing s1 over to this s2 variable is the same as me moving this s1 variable to s2. I still cannot use this s1 variable anymore because it has been moved to this s2 variable. Let's see that in action. Let's try to code that. What I'm saying is, okay, let's say we have s1 equal to this in a main function, and s2 equal to a1.clone, everything is fine. Or sorry, s1.clone, everything is fine. You have two different places in memory, or two different hello variables, or sorry, Harkiyat variables, one in one place in memory, other in another place in memory. Now I say, let me define a function called do something that does something with a string. It takes a string as an input. Let's call that string s2 for now, and does nothing, just prints it. I've just defined a function right now. When I do this, does the Rust compiler begin to complain? It does. What does it say? It says s1 has been moved to s2. ये जो value है, this value is now owned by s2. s1 is invalid. The same thing happens if I don't do this. When I do this, do underscore something of s1. I'm not doing this. I'm not saying let s2 equal to s1. But I'm calling a function where I've defined another variable s2, which is pretty much doing the same thing. s2 is becoming equivalent to s1. So this s2 now owns that value. This variable that now exists in this function owns that value. s1 is again not valid. s1 is again invalid. If you try to use just s1 over here, s2 does not exist. If you try to use s1 over here, then it will again complain with the same error. Borrow of moved value s1. Harkirat, I did not move s1 to s2 over here. You did not in this line of code, but you did in this line of code. In this line of code, you said I take s2 as an input. You passed s1 string over there. So, it is the same as me doing something like this. Let s2 equal to s1. Passing something as an argument is the same as, taking this variable over here, s1, and putting it over here in a different variable called s2. So the same thing happens if I write this line of code, or if I take s2 as an input over here and pass s1. So still gets moved over to another variable. And as you can guess, whenever this other variable goes out of scope, which is right here, the memory gets cleaned up. The ownership rule says whoever owns the actual data on the heap, which is yahan pe the owner of this data is s1. But after this line of code, the owner of this data becomes s2. At this line of code, that s2 variable goes out of scope. Over here, the data has already been cleaned, which is why it makes sense for s1 to throw an error at compilation. Okay, this code is wrong. The data will get cleaned from the heap directly over here. Please don't try to use it over here. If I try to run this, you'll get a similar error. And this is sort of the, there you go. Gives you a way to fix it as well. But what does it say? It says borrow of moved value s1. It says you're trying to move s1 into this function. It will not work. And can you fix it? Yes, it's giving you one way to fix it, which is, just clone the string. It is also telling you the one unoptimal way to fix this, which is just clone it. Okay, theek, this will have a copy of s1. It will not have the original variable. Then everything is fine. It will work. That is why I said, you will do this in Rust initially. You will see this error. You will look at the compilation help. You will just clone the string. You will do this a lot of times initially. Just keep cloning things, which is fine. But when you're writing very memory safe code, you don't want to take too much memory. Then of course you need to figure out how can you satisfy the ownership rules yet not clone the string. We'll get to how we do that very soon. But is this clear? Do we understand ownership rules? I know it's hard. It's probably the hardest thing to digest initially, which is moving variables and both into a function and into another variable. To recap, what does it say? This specific thing will fail if you try to take s1 and pass it to a function. s2 will take ownership of it, which means s1 is no longer valid. But you can do one more thing. What you can do is you can pass back ownership of that variable. So you can return s2 over here. Sorry about that, I wasn't recording. I was saying you can return s2 back over here, or sorry, a string back from this function. And over here you can be like return back s2, and you can say s1 equal to do underscore something of s1. Basically, you take this thing is stored on the heap. This Harkirath thing is stored on the heap somewhere. Who is the initial owner of this? It is s1. On this line of code, the owner is s1. Then do underscore something gets called. Ownership gets moved to which guy? Ownership gets moved to s2. s2 is what owns this Harkirath value over here. We return back s2 variable to s1 over here. So who becomes the owner of this value now? It becomes s1. If you return s2, the ownership gets moved back to this s1 variable. It doesn't work right now because s1 isn't mutable. But if I make s1 mutable, then I can pass ownership here, do underscore something, can borrow it for a while, and keep it. This isn't borrowing, this is moving only. I moved the ownership over here. Ownership gets moved over here. It does its thing with s2. It returns s2 back to the original implementation, and the s1 variable can store that value. You can finally print it. This is the same as doing this. If this feels complicated, then let me just remove this. What happens when I do this? Let mute s2 equal to this thing. Then s1 equal to this thing. Then let s2 equal to s1. Then s1 equal to s2. Who is the owner of the Harkirath string over here? It is s1. Who is the owner on this line? It is s2. Who is the owner after this line? It is s1 again. So s1 is again valid after this line of code. S1 is again valid after this line of code. If I try to print s1, I have no compilation errors. But can I print s2? Is s2 valid after this line of code? The answer is no. s2 has been moved. The value of s2 has been moved to s1 again, which is why if I try to print s2, it says it is no longer valid, borrow of a moved value s2. So do we understand moving a value? There can be a single owner of a value. If you ever assign that value to a different value, then s2 has, in this case, s2 becomes the owner of the string, and then again s1 becomes the owner of the string. You keep on moving the ownership of the string. If you don't understand this, you should go to our original Rust Bootcamp video where I cover this with a very weird example. Alrighty, moving on. We hopefully understand ownership. We hopefully understand moving. Next up, we need to understand borrowing and references. Let's get into them one by one. All right. Hopefully we understand ownership and borrowing. Ownership is any value that's on the heap is owned by someone. Whenever they move out of scope, the value gets removed from the heap as well. Moving is a lot of times when you define a variable equal to another variable, you move over the ownership of the underlying value to the new variable. Next up is borrowing and references. Let's see why do we need them and where they are useful. This code that you see on the right is ugly. You have to return the value back. The code that we wrote, you can look at this code, does the same thing, which is the main function calls create underscore string, which first has a variable called s1, which has the ownership of this hello value. Then it calls a print underscore str function. So the ownership gets moved to this s2 value. Then the ownership gets returned from this back to this s1 variable. That is how we have carried over the ownership of this s1 variable, or more specifically this hello value throughout. But why have we done that? Let's say we want to use s1 again. We want to call this function. After that, we want to reuse s1, which is why we had to move back the ownership. If we did not need to use s1 after this, then there is no need to return s2 here as well. s2 can exist independently on the heap. But this code is ugly, remembering to pass in a value, then returning back the value, then reassigning it to the original variable. What if there was an easier way to do it? And the answer is you can do it by using something called references and borrowing. We can pass in a reference to s1. s1 is borrowed by print underscore str. s1 is still owned by create underscore string, or more specifically the s1 variable. This is incorrect. They should say s1. What we're doing over here, what we're saying is, let me just start to code this. I think we can understand this a little bit better over here. Okay, this is how we had done the original implementation. Hopefully you understand the code that is written over here. The code says, define a mutable variable s1. s1 owns the value. What is the value? It is this Harkirath string that exists on the heap. Who owns the value over here? When do underscore something gets called, then s2 owns the value. On this line of code, s2 owns the value. Then whenever you come back here, we reassign the value to s1. So s1 owns the value again. And then over here we print S1, everything is fine, compiler does not complain. On this line of code, S1 gets cleared. But what if you don't want to do this ugly logic of first making the string mutable, then reassigning the string? What if you want to retain ownership over here? How can you do that? How can you pass something else to a function so that you don't pass in the ownership? You just borrow or lend the variable. The variable gets lent over to the function. The function that wants it borrows the variable, does whatever it wants to do with it, and eventually the ownership remains with S1. If I change the code just a little bit where I say, okay, hey, do underscore something. I don't want to pass you S1. I don't want to pass you the ownership. S2 will not be an owner of this value. I want you to borrow S1. I am giving you a reference to S1. You can use S1 freely, no problems over there. You don't have to return it to me either. I am still the owner of S1. Think of this S1 variable as a bap variable. I still own the value. I am allowing you to borrow it, do whatever you want to with it. And then eventually I will still be the owner. The value will only get cleared from the heap when this function ends. Isn't this syntax slightly cleaner than passing over ownership and then passing back ownership and then printing S1 over here? Looks like it. So these are what are called references, and the process, what you're passing over here is, this is what is called a string slice. We'll be getting to this in the advanced part, but think of this like, you're passing it an address or a pointer to the S1 variable, which you can use here. You can dereference. If you come from the C++ world, you can dereference S2 over here. Even if you don't understand dereferencing, it's fine. This macro automatically dereferences it. The point is, I'm not passing in the S1 variable. I don't want to give away my girlfriend to you. You can borrow them for a while. This example is covered in a little more detail in the main video. It's like a bad way to put it, but you get the idea. Okay, borrow the variable, do whatever you want with it. You don't have to return it to me. I still own the thing, and I can still use it over here. Cool. Hopefully that's clear. What does borrowing mean? Whenever you pass a reference to S1, it means do underscore something has borrowed. This value hasn't moved to this function. This value isn't moved to the S2 variable. It has been borrowed by the S2 variable. You can still use it after it. The owner of S1 owner of this value remains S1 throughout. Over here, over here, over here, over here, over here. Every line of code pay, owner of this is S1. It is being borrowed by a few variables from time to time. The only difference, if you look at the code, is that you're passing in a reference to S1 over here, and then as the argument, you are not expecting a string, you are expecting a reference to the string. When you do not borrow, when you write code like this, yeah, there's another thing. I mean, we were using very complicated functions right now. You can also do this. If you remember our original example, let S2 equal to S1. What did we saw at this point? Okay, I was not able to print S1. It gave me an error. Why? Because S1 became invalid over here. But just like I was passing in a reference to a function, I can just define a variable here which is a reference to it. I can also, do a function call. Rather than doing this, I can do a function call and pass in S1. Or I can say, let S2 equal to @S1. If I want to do something here with it. If I want to define two variables that both are sort of pointing to the same thing, but the owner remains single. There is a single owner of it, but S2 can point to it. Then I can do it directly in the main function. I can also define a separate function like we did. Then I print the value of S1 and S2. This is valid code. This is invalid code because here I move the value of Harkirat over to S2. Here I just borrow the value. Owner still remains S1. Owner is still valid, which is why this line of code works. This much code does not work. Cool. Alrighty. Look at it. What code works over here? The code that works is when you define let S2 equal to @S1, because you are borrowing S1 in S2, owner is still valid. What code does not work? When you say let S2 equal to S1, S2 becomes the owner of this value. S1 becomes invalid, and hence you cannot print S1 over here. That's exactly the error that you see over here. Why is Rust forcing us to do so many things? Memory safety, right? If Rust can ensure there is a single owner at a time by forcing you to write code like this, कि यार मैं तो compile ही नहीं करूँगा. I will not compile the code if you try to use S1 over here. I will invalidate S1 because I don't want two owners at the same time. Yaar. If there are two owners of this hello value, then when will I know when to clear this? You might say, Kirat, the compiler should be smart enough to know okay, if S1 has gone out of scope and S2 has gone out of scope, then it should clear the value from the heap. The answer is yes, but that is sort of what garbage collectors do. But we want to stay away from that complexity. We don't want the compiler to spend a lot of time figuring out how many references are there to something, when should I clean it up, which is why we don't want a garbage collector. We just force. Solana blockchain and Rust have a lot of parallels this way. They force you to write very difficult code so that the final thing can be very optimum. I repeat, slight detour for a minute. But whenever you write a Solana contract in the future, whenever you do a Solana RPC call, you will notice the way you have to, send data is sending a bunch of accounts upfront specifying signers, some extra thing you have to do, which you don't have to do in Ethereum, because it makes the final process really fast. Whenever the miners are running your code, they can decide to parallelly run based on what inputs you provide. As the developer, this makes your life hell trying to figure out what inputs you have to give, but it makes Solana really fast. Similarly, as the developer, Rust makes your life hell. You can't do such a simple thing which every other language will provide you, but Rust will be like, no, I have ownership rules. You'll be for fighting the what's called ownership rules, fighting the borrow checker, trying to figure out where did I go wrong, what thing got borrowed, and why is this variable moved, why is this variable invalid. And the answer is, the compiler is just saying upfront, bhai, this is how I work. Ownership rules work a certain way. If you want this code to work, either clone the string or, use references, that is fine. But don't point two owners to the same value. I will not let you. Cool. That is what borrowing is, what is happening on the right over here. Rather than doing let S2 equal to S1, I'm doing let S2 equal to at S1. Question is, how can you create a mutable reference? What if you want to borrow and mutate the value? You want to borrow the value and also change the value in there. Can you do that? The answer is yes. How can you do that? Pretty simple. Rather than passing at S1, you have to pass at mute of S1. Rather than expecting at S1, you expect at mute of S1. So if I go back to the code over here, let me revert this to the original functions that we had. If you want to change this S2 string right now, if we try to change it, S2 dot push underscore str hello, or Harkirat hai to sing, it will tell you okay, you're trying to cannot borrow S2 as mutable because it is behind an at reference and not behind a at mute reference. This needs to be a mutable reference. Whenever you're passing it, you need to pass in a mutable reference, which means the S1 variable needs to be mutable. If you change these three things, as you can see, compiler stops to complain. What have I changed? Number one, I made S1 mutable. Number two, whenever I was passing, I pass in a mutable reference now. Okay, you can borrow and make changes to it. It is fine. That is what is happening here. S2 dot push underscore str will be able to push to the string. If I print the string finally, it will be Harkirat space sing that is printed over here. Let's see if that happens or not. If I run this, the thing that gets printed is Harkirat space sing. All right, great. Over here also and over here also. That's how you take a mutable reference. And another set of ownership borrowing rules that Rust enforces on you is at any given time, you can have either one mutable reference or any number of immutable references. I repeat, at any given time, you can have either one mutable reference or any number of immutable references. The Rust compiler says, okay, you are creating references left, right, and center. That is fine. You can do it. Let S2 equal to at S1. Let S3 equal to AWS key service at S1. Both of these are immutable references to S1. And if I try to print all three of these, everything just works as expected and nothing out of the ordinary over here. No compilation errors. If I run this, I see the thing printed thrice. But if I make one of these, I repeat, if there is even one mutable reference, then I cannot have an immutable reference. If there is one thing that is changing the value on the heap, there shouldn't be another thing trying to read the value. That can also lead to memory issues. What if you're expecting some data to be there and immediately someone muted it? That data sort of changed. So to ensure memory safety, the Rust compiler says here multiple people can read from the same place in memory, that is fine. But if even one is trying to change data over there, if there is a mutable reference, then I will not allow other mutable or immutable references. I cannot have another mutable reference or another immutable reference. If there is one currently active mutable reference, what does it say? Can't borrow S1 as immutable because it is also borrowed as mutable. What is the compiler telling you? It is telling you that this does not follow this specific ownership rule. What was the rule? Okay, at any given time, you can have either one mutable reference or any number of immutable references. You can have multiple immutable references, that is fine. As soon as you introduce just one mutable reference, you cannot have other immutable references. The code will begin to complain. This is similar to if you might have seen in databases, if this is a database, there can be multiple reads at the same time. And whenever you try to write, you have a write lock, but not a read lock. Whenever you're trying to write from here, you lock the specific row in a database. Reads are still allowed on that row, but you don't allow another person to write on that row to ensure, two people aren't overwriting each other. Similarly here, if you are mutating it once, if you have one mutable reference, you cannot have another immutable reference or mutable reference. This is what the ownership rule says. Why does ownership rule do this, Arkirat? For memory safety. It will force you, I know you have to write extremely tough code. The Rust compiler says, yes, I'm forcing you to write code a certain way, but I will promise you, if you write code this way, somehow figure out how to make this work, then your final code will not have memory issues. It forces you to write code in a way. The ownership rules will give you so many compilation errors. Okay, by the end of it, the code that you have written after fixing all of these errors will not have any memory issues because it isn't allowing two mutable references. It isn't allowing two owners. It is making sure whenever the value that is owning the data gets moved out of scope, the data also gets removed from the heap. So it does all of these things to do very efficient memory management. And you as the developer don't have to worry about memory management. You do have to worry about fighting the borrow checker and making sure you're not doing anything weird and making sure the compilation succeeds. If your compilation succeeds, most probably the code that you've written will work. Cool. Alrighty. Okie dokie. That's all I had. Let me just take you through a visualization of this. I define a mutable variable over here called S1, and then I take a mutable reference in S2. Then I try to mutate it again. It'll throw an error. This line of code is enough to throw an error. What does it say? The error says second mutable borrow occurs over here. Cannot borrow S1 as mutable more than once at a time. If I try to borrow it as mutable over here as well as over here, the compiler will fail. I won't be able to compile my program. That covers all the jargon we need. Hopefully that was easy enough. We're done with part 1. Let's move on to part 2, where we're going to cover some, I would say these are simple enough. This is going to boggle your head a little. Traits are, I don't know why I marked them as red. They're probably orange. Multi-threading is also not too difficult. Macros, the thing that we're doing is probably not going to be too difficult. This we're probably going to skip, and lifetimes. This is probably the only hard bit after this. If you understand everything else, lifetimes is the only thing that are going to boggle your head. Everything else should be straightforward. With that, I will see you in part 2. All right, let's get into the advanced bit now. I wouldn't call it too advanced. Some of the things here are fairly simple. The things that are specifically mentioned in green are much simple, like very basic data structures. Only they're stored on the heap, which is why we're discussing them separately. Then we'll understand the difference between strings and slices. This is probably a good thing for you to know. Then generics, that's also not too difficult. Traits, fairly simple. I don't know why it's mentioned in the red. Multi-threading, macros, futures, async await, and lifetimes. Only this part I'm not sure of. Most probably this will be covered in a separate video. We will see by the end of it. Without any further ado, let's get into the very first section, which is on collections. What are collections? I'm sure you can already imagine / guess. Arrays, vectors, dynamically sizable vectors, hash maps, things that dynamically increase and decrease in size, where you can store a lot of data together, is what is known as collections. Rust standard library includes a number of very useful data structures called collections. Most other data types represent one specific value, but a collection can contain multiple values, just like an array. The data these collections point to is stored on the heap. Why? Because again, very similar to a string, this is dynamic data. It can increase and decrease in length. Hence, it should be stored on the heap and not on the stack. The very first one that we're discussing is vectors. All right, let's get into vectors next. Vectors are very similar to vectors in C++, basically a dynamic array that you can push elements to pop elements from. A vector allows you to store more than one value in a single data structure that puts all of the values next to each other in memory. Basically, whenever you are using a vector, it is similar to you creating a string. If this is the stack and this is the heap, if you have a string variable, the variable is stored on the stack over here, which points to some data on the heap. And similarly, if you have a collection, if you have a vector, you will have a variable over here which points to data on the heap, where you will have, let's say, multiple values 1, 2, 3, 4, 5, an array like this. It is just a vector or an array that can increase and decrease its size. You can add elements to it, remove elements from it, and hence it is stored where? It is stored on the heap and not on the stack. This is the syntax to create a vector and push some elements to it, print the final vector over here. The only weird thing that you might find is this syntax to print the vector. Let's really try to code it, understand how can you print various values, what is this extra thing. But other than that, I would assume the rest of it is fairly straightforward. Let vec equal to vec : new. This will initialize a new vector, and then let me push a few values to it to make it mutable. This is very similar to the code that was written in the slides. The only thing is, when I'm printing it, I'm writing double quotes just like we did until now. But unfortunately, vector, if you look at it, is a struct in itself. And if you remember, you can't really print structs automatically. You can print the value inside a struct, You can get the value at the 0th index and print that. But you can't print the vector as such unless they do something called implementing a debug trait. Harkirat, what is implementing a debug trait? We'll get to when we reach the traits section. But basically, from time to time, initially when you're going through Rust, you will try to print a statement like this. And if it doesn't work, if it gives you an error, add this : over here and hope that the thing that you're trying to print does implement the debug trait. If it doesn't, then of course this will fail as well. You'll have to figure out a different way to print the element by, let's say, iterating over the vector. But thankfully, this vector trait, whoever has written that, implements something called the debug trait. Basically, has an implementation block like this, where there is a function called debug, where it is defined how this specific vector should be printed, which probably means, printing 1 and then comma 2. But if you don't understand this, this is fine. This is just the way to print vectors for you for now. If you want to print the complete vector object, rather than writing print braces, you have to add a : in here. If I try to run it, you will see 1, 2 gets printed on the screen. This is a mutable vector, which is why I could push elements to it. If I make it immutable, then I won't be able to. Fairly simple stuff, nothing too out of the ordinary. The question is, how can you get values inside a vector? How can you index the first element, the second element, so on and so forth? And this is where, let's sort of solve this via assignments. The very first assignment is, can you write a function that takes a vector as an input and returns a vector with even values from it? It takes a vector as an input, returns another vector which has only the even values. So for example, over here I have a vector that has two values. It has 1, 2. And we want to create a function even underscore filter, let's say, that takes a vector as the input and returns another vector with just the even values. So how can you do it? We need to understand, number one, how to iterate through a vector, and number two, how to, create a fresh vector and push elements in there. I guess that's probably the easy bit. Approach number one that I'm taking, I'm defining a new vector over here. And I'm iterating over the original vector, whatever I got as an input in here. Notice, there's already some errors over here. It is already telling you here this syntax is incorrect. It says add missing generic argument. We will get to this when we reach generics. But for now, you have to know that you can't write vec over here. You have to write vec of i32. You basically have to tell what kind of a vector is it. Is it a vector of numbers? Is it a vector of strings? And the way to do that is by specifying a generic argument. What is a generic argument? We will be getting to very soon. Vector of i32, new vector is vector : new. For val in vec, if val mod 2 is 0, then you do a new underscore vec dot push val, then you return new underscore vec. Make sure it is mutable. Change the return type of the function to be vec i32. Hopefully that is straightforward. I've written a function which takes a vector as an input. The type of the vector can be a little overwhelming right now. Vec of i32, it's basically a vector of type number or of type i32, and it returns another vector of type i32. I define a new variable here called new underscore vector. I initialize it to an empty vector. I iterate over the original vector. This is one of many ways to iterate over a vector. We'll be coming to more ways very soon when we reach the iterator section. But one of the simplest thing you can do if you want to iterate over a vector is for val in the original vector. This will let you iterate over all the values. And over here you check, is the current value modulo 2 equal to 0? Is this an even value? If it is, you push it to the new vec array. You return this new vec array from here. And now if I call even underscore filter of new vec on the vec over here, hopefully it should just print the even values. So if I have 3 values in the original array, 1, 2, and 3, it should only print an array which has a single value called 2. And that is exactly what happened. Hopefully my function works as expected. I have written a function that iterates over all the values of this new underscore vec and this original vec and pushes just the even values to this new vec variable. This is one way to do it. And if you remember, what is a vector? It is stored on the heap. What am I doing here? I am passing the ownership to the vec even underscore filter function. If I write code that looks like this, let answer equal to this and print answer over here, I am passing the ownership of vec to this even underscore filter function, which is why if I try to use vec again, will I be able to do it? Go back to the ownership section. I cannot. What does it say? Borrow of a moved value vec. This vec variable I moved into this even underscore filter function, which is why I cannot use it anymore. How can I make it usable after this? By passing in a reference, not pass in a vector, but at vector. This vector that we have over here is a reference to the thing. It is borrowing the vector. It is not actually owning the vector. The ownership remains in this vec variable, which is why I can now print it over here. I can use it after this line of code. But if I pass in the value, if I pass in the ownership, I won't be able to. Cool. Let's run cargo run again and see if it works. It does not work because I have to dereference the value over here. This is basically a pointer to the number. So I have to do something like this. I have to dereference the number before pushing it. And now if I see, this is the original array printed after the evenly filtered array. Cool. This is the evenly filtered array. This is the original array that gets printed on the screen. And now I have passed a reference to vec i32, just like in the last few slides. If you remember, we were passing a reference to the string rather than passing the whole string. Vectors and strings are very similar. Strings are actually vectors only, right? There are a bunch of characters one after the other. Similarly, right now we have a bunch of numbers, but if I change this to be a character array, then a vector can pretty much just be very similar to, if not exactly the same as a string. A vector is nothing but, or a string is nothing but a vector where every element is, a character rather than being a number. Cool. Let's go to the slides. Let's look at both of these implementations here. Pretty much the same thing. Define the vector over here, call the even underscore values function with, firstly, this is the third approach, which is I pass the original vector inside. I pass the original vector inside mutably. I pass in a mutable reference over here. If you look at it, what is the argument over here? It is a mutable reference to vec i32. And I just remove the elements from that specific index that is an odd number. I repeat, anytime there is an odd number, while I is less than v dot length. Very different syntax have used over here. I'm not iterating like that. This is probably an easier iterator for you to understand. I initialize a variable called I. I say while I is less than v dot length, while I'm iterating from I to I equal to 0 to v dot length minus 1. If v of I modulo 2 is not equal to 0, if this is an odd number, then I remove it from the index or remove it from the vector. Else I do I equal to I plus 1. That is how I'm filtering out the array. This is another way to do it. And I'm doing it in place. I am not creating a fresh array. Over here, I was creating a fresh array. We have two arrays in memory at some point. I create a fresh new underscore vec over here. Versus in this approach, I have a mutable reference to the original vector over here, which means I'm just changing it in place. I'm not creating a fresh array. This is more space efficient compared to our approach. That's approach number 1. And approach number 2 is just, me taking the ownership of the vector, me creating a fresh vector over here, and then pretty much the same as the approach that we had written over here. So do we understand vectors? Do we understand how can you get a specific value at a specific index in a vector v of I? Do we understand how can we remove an element from a vector v dot remove? How can we push an element to a vector v dot push? Are we good to go? Hopefully that's clear. And one more thing is how, just another way to initialize a vector is by using the vec macro. Again, I'm introducing a term we haven't yet learned, which is a macro. But as the name suggests, it's something that expands to something else. It is a macro which expands to something else. This vec exclamation 1, 2, 3 will pretty much create a fresh array or a fresh vector for us and push all of these 3 elements to it. This is just a easier way to initialize a vector. Rather than me having to write this, I can simply write vec exclamation 1, 2, 3, and this will initialize a vector for me. That has these 3 values, 1, 2, 3 as the initial set of values. It's just another way to initialize an array. And now comes the slightly hard bit inside vectors, which is why I've put an orange thing over here. Defining the type of the vector as a generic. I have already done it, so hopefully this is not too hard. But whenever you are defining a variable, a vector, its type can be inferred, or you can explicitly give it a type. And if it is a vector of integers, then it looks something like this: vec I32. That is the type of this numbers array. It is an array, or it is a vector of type numbers I32. It can automatically be inferred. I repeat, whenever you're creating any variable, let me delete all of this. Whenever you're creating any variable, let's say let x equal to 1, its type is automatically inferred. The Rust compiler automatically understands that this is a number, so probably I32 is its type. What is its type? Its type is I32. Did I have to explicitly give it a type? I did not. I can give it a type if I want, but I did not have to explicitly do it. Similarly, when you're defining a vector, my underscore vec, you can define it like this, and its type will be automatically inferred. I repeat, its type will be automatically inferred to be vec of I32, which means a vector of numbers, or if you want, you can explicitly give it this value as well. Something like this. Again, I understand if you don't yet get what this syntax is, we'll be reaching generics very soon. Then you'll be able to comprehend this, angle braces a little bit better. Alrighty. With that, we'll move on to hash maps, which is the second type of, very commonly used collection in various languages. All right, let's understand hash maps next. I'm assuming this is fairly simple if you come from the Java world, JavaScript, any language, I would say. There's this concept of hash maps in Java as well. There's this concept of maps in C++. Similarly, in case of Rust, hash maps exist. What do they let you do? They let you store key value pairs in Rust. Until now, we have stored collections like this. We created a vector that had values like this: 1, 2, 3, 4, 5. What is a hash map? A hash map is a key value pair, which means it has a key like Harkirat and has a corresponding value for Harkirat, let's say 21. Let's say this is the age of Harkirat, let's say. Then there is another user called Raman, and this is the age of Raman. Then there is another user called Parthav. weirdest name I could think of. Let's say their name, age is 32, so on and so forth. This is again a collection. It has various values inside, but every value is a key value pair. Along with the value that you have on the right, there is a corresponding key over here. You can insert values in this hash map. You can get values from this hash map. You can clear the whole hash map if you want. There are various functions that the hash map struct provides you. Let's look at them. The common ones are insert, get, remove, and clear. This would let you insert something in the hash map. This would let you get something from a hash map given a key. Remove something from a hash map, clear something from a hash map. There is some code written over here that will be a little hard to digest, so I have written it over here as well. Let's kick things off by understanding how do you define a hash map. The way to define a hash map is, number one, you have to import it from one of the standard libraries in Rust. So you have to add the import statement at the top of your file. Use std : collections : hash map. Then this is how you declare your very first hash map. This is similar to how we had declared a vector before this, vec : new. This is how we were defining a vector. This is how I have defined my hash map. Do I need to give it a type over here? I don't. So, if what was written before feels a little weird, here is the simplest way to define a hash map. Let mute users. It needs to be mutable if you need to insert some values inside it. Hence, this is a mutable variable.